We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science.
It holds opportunities for us to make discoveries about our home planet, about our sun.
Thought and action. Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort,
Woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish a community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp,
positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect descending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water.
And refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon, capable of supporting a growing community of efforts.
And we will expand the logistics supply chain to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy, but nothing in our history ever has been.
The Eagle has landed. We got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
Well, good morning, everyone watching online. Thank you for watching our 2022 NASA Lunabotics competition here on a Tuesday morning. I apologize for the noise, but this is a real working robotics pit that I am broadcasting from right now. In a minute, I'm going to go back to our broadcast center, which is a little quieter. But I just wanted to show you the hustle and bustle. These students are working really hard this morning to get their robots ready to compete. And so you're getting a live view of our robot pit, and you're only being able to see in this camera view about half of the teams that are working here in the robo pits this morning. All these teams have traveled from their universities from all around the country to compete in NASA's Lunabotics 2022 competition at the Kennedy Space Center in Florida this week. My name is Kurt Lloyd. I'm a NASA software engineer, and I'm going to be hosting the live stream and trying to explain to the best of my abilities what you're seeing on the screen during the competition. So we will be back in just a minute with more information as you watch the students get their robots ready to compete this morning. Thanks for watching, and don't go anywhere. As you see on the screen, students are busily working on their robots in their pits. And for those that are joining us and are interested when their favorite team is going to be competing, at the bottom of the hour, which will be 8:30 Eastern time, what I'm told, and caveat, this is subject to change. Our schedule is very fluid, very flexible. But what I'm being told is our first two teams that are going to run in our simulated regolith arena are University of Rochester and the University of Akron. And if all things go smoothly this morning with the team's preparations, they will start at the bottom of the hour, which is 8:30 a.m. Eastern time. After that, we're told we will see Purdue and New Mexico Tech. And after that, we're told that we will see Arkansas. Keep in mind, though, that our schedule is very fluid, and as the schedule changes, we will try and stay on top of that and try and announce as quickly as we find out changes. We'll try to announce those on our live stream. So for those that are watching the stream and may not be familiar with our competition, we are back after a few years of not being able to put on this competition. We are the NASA Lunabotics Artemis Student Challenge, and we're holding this event at the Kennedy Space Center Visitor Complex in sunny Central Florida. And this year we're super excited because it's the very first year where we are holding this event and having these robots compete in our brand new indoor Artemis Arena. In past years, we have had to temporarily create an arena outdoors and cover it in a tent. And it was a really great facility, but because it was a temporary facility, we were not allowed to compete anytime there was any lightning anywhere near the Kennedy Space Center Visitor Complex. But now that we have our arena indoors in a permanent facility, the storms that pop up in Central Florida this time of year are not going to be interrupting our competition. So for anyone who's not familiar with our event, our competition, Lunabotics is a collegiate level robotics competition. And these robots in our competition, they are tasked with navigating around an arena that we have filled with crushed volcanic rock. And that crushed volcanic rock simulates moon dirt to these robots. These robots have to avoid craters, they have to avoid rocks, if necessary. Obviously, if a robot is able to drive through a crater and drive over a rock, then they wouldn't need to worry about avoiding it. Once they get past the craters and the rocks, their job is to dig down beneath the surface into the crushed volcanic rock, which simulates the dry, fluffy soil on the moon. Fluffy soil on the moon, we like to call regolith. So you may hear that word a lot during this broadcast. And regolith is a word for moon dust or moon dirt. Once they dig into the crushed volcanic rock, their task is to really dig very deeply into the soil in order to find the buried gravel that we've put beneath. And this buried gravel will simulate to these robots frozen water that's hiding beneath the surface on the moon. And it's the frozen water or buried gravel rock that these robots are tasked with bringing up to the surface, carrying on board, and carrying it back to the starting block, which simulates the lander that brought the robot to the surface of the moon. But that's not the end. They don't just bring it back to the lander. They have to deposit the gravel rock onto the lander. They have to dump that simulated frozen water into the lander's hopper. Once they've done that, our judges will weigh all of the rocks that the robots have brought back, and teams will be scored based on the weight of the gravel rock that they bring back. But really, that's just the tip of the iceberg, because this competition, this entire Lunabotics competition, is not just about how much rock these robots bring back. These teams are also scored, judged and scored on a lot of different variables. They've had to submit project management plans, systems engineering papers, public outreach project reports, and they also get judged during this mining portion of the event. They also get judged on how much power the robot uses during its run. They get judged on how much their robot weighs. They get judged on how much bandwidth is used in their communication during their run. They get judged on so many variables. It's not just simply a matter of the robot that brings back the most rock wins. It's not that simple. It's a very complex and very challenging task. What we have scheduled for today is to give our teams that were that did not get a chance to have a first attempt in our mining arena, we're going to give those teams their first attempts this morning. And as soon as we're done with giving everybody their first attempt, the first judged and scored official competition attempt, then we will basically start over and let all of these teams run their second runs, their second judged competition attempts in the arenas today. So that is our plan. We're going to try and get everybody through as quickly as we can. And what we have coming up first is Rochester and Akron. After that, we'll have Purdue and New Mexico Tech. After that, we will have University of Arkansas and possibly an empty slot, not sure yet. And then after that, we will basically run everyone who's here. We have nearly 40 teams total that will be competing this week. Due to some COVID protocols that are still sticking around, we have decided to split those nearly 40 teams into two groups. Group one that you're seeing here competing yesterday and today, and then group two, which will come on the NASA's Kennedy Space Center Visitor Center on Wednesday. We won't be live streaming on Wednesday because Wednesday is just a setup day. Those teams, group two, will be competing, and we will be live streaming that competition on Thursday and on Friday. So just to summarize, we live streamed yesterday, we're live streaming today, and we're going to take a break from the live streaming on Wednesday, and we'll live stream again on Thursday and Friday. Each day has a different URL for our live stream. So in order to make sure you click on the proper URL, make sure you go to either our Facebook page where all four of those URLs are advertised, or go to our main Lunabotics webpage, which is nasa.gov/Lunabotics, and you should be able to click on the current live stream right there on that page. Some of our viewers may be wondering why we're even doing a competition like this. Why does NASA even in the mining business? Well, that's a really good question. The answer is that NASA's plans for long-term sustainable human missions on the lunar surface, those plans are going to require new ways of thinking and new technologies. We're going to need to use the resources that we find on the surface of the moon in order to save the mass and the energy and the funding that's required to ship tons and tons of resources from the surface of the Earth. We can use the soil on the moon, called regolith, for construction projects. But hiding beneath that lunar soil, or regolith, is frozen water, which in that environment is like a gold mine. NASA organizes and executes an event like this because it has long-term benefits for everyone involved. NASA directly benefits by assessing student designs and the resultant data the same way it does for its own less frequent robotic prototypes. This competition encourages innovation, and it encourages out-of-the-box thinking, which could lead to clever design solutions to the many challenges inherent in future Artemis missions. Advances in off-world mining and off-world construction technologies could actually present advances in related Earth-based technologies. And the competing students in this event, they gain skills in robotics, in engineering design, and in systems engineering principles that are going to translate to any industry that these students end up working in after they graduate.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Broadcasting live from the Kennedy Space Center Visitor Complex. This is NASA's Lunabotics 2022 event. I just got a schedule update, and it looks like the first two teams this morning are going to be Purdue and New Mexico Tech. Again, that's Purdue and New Mexico Tech are going to go first today, and then Arkansas will go second. And stay tuned for live schedule updates because this is a very fluid and changing schedule. We are broadcasting live, Lunabotics 2022. I was just in the pits, and it looked like the Purdue students were getting suited up in their protective equipment in order to take the robot into the arena. So stick with us, and we will switch to the arena cameras as soon as we see some activity with students in the arenas. And actually, on the screen on the far upper right, you can see some other students. Those may be the New Mexico students. I'm not sure, suiting up for their run. So stay tuned because students are getting ready. They're getting their robots ready, and they're getting their equipment ready for the first run, which is going to be Purdue and New Mexico Tech. I mentioned earlier that my name is Kurt Lloyd, and I'm a NASA engineer. I've been working at NASA since the early 90s. I started as an intern and was lucky enough to be hired after my internship ended. And I spend I spend my days working in a group at NASA Kennedy Space Center. We like to call ourselves SwampWorks. And what we do in SwampWorks is we research and develop technologies for long-term human exploration of the moon and eventually Mars. We research and develop um, technologies such as excavation technologies, ground clearing and site preparation, construction, additive manufacturing, dust mitigation, resource processing, and resource utilization, and more. And that's why the folks at SwampWorks, myself, and a lot of my coworkers are heavily involved in the Lunabotics event each year, because it perfectly aligns with the work that we're doing and the research and development that we do in our group. What you're going to see by watching these robots competing this week on our live stream is you're going to see a lot of different robot design trade-offs. These students have looked at the challenge, they've studied what these robots need to do, and they've come up with solutions that they think solve the challenge in the most appropriate way. There are lots of different ways to excavate. And so you'll see in this event, you'll see some bucket or backhoe style excavators. You'll see some auger designs. You'll see some bucket ladders or bucket drum systems. You might even see some rakers or some pneumatic excavation designs. But these robots do more than just dig. They they have to move across the surface of this. It's a unique material. This crushed volcanic rock. It's light and fluffy on top, but it's hard packed underneath, and so you will see robots that are trying different types of locomotion designs. You'll see wheels, you'll see tracks, you might even see pontoons or screws used for locomotion in this competition. And once the teams have driven across the surface, dug down really deep, and mined down to the gravel that we've hidden beneath the surface, and driven back to the starting spot, they actually have to offload that gravel onto our simulated lander. And so you're going to see different dumping mechanism designs. You're going to see conveyors. You might see augers. You'll see dump beds, like a dump truck that actually lifts up. And that's actually not all. I've basically described all the different mechanical systems on board these robots, but what's kind of hiding underneath the hood of all these robots is a computing platform and sensors and possibly some autonomy and a lot of software in some cases. So you're going to see a wide variety of different designs, different styles of solutions to the problem that we've given to these teams this week by watching these live streams. We apologize for that. While we wait for that site to get updated, you can tell people to find the link for all 4 days of our broadcast by going to our Facebook page. They can go to Facebook, they can search for NASA Lunabotics, and our Lunabotics webpage or Facebook page will come up. You only have to scroll down 4 posts before you find all 4 links to all 4 days' broadcasts there on our Facebook page. So thank you for helping us spread the word and spread these URLs for our live streams this week. We really appreciate you sharing this event with your friends and family back home, and maybe your classmates and teammates who were not able to be here live in person with us. You're watching NASA's Lunabotics 2022 competition, about ready to get started on day 2 of 4 days here at the Kennedy Space Center Visitor Complex in Florida. In this view, you can see 4 live cameras from our Artemis Arena, where our students are going to be deploying their robots as if they had just landed on the lunar surface. And in the background, you can see one of our student teams has entered the room. They're wearing white bunny suits, we like to call them. These white suits protect their skin from any irritation that might come from getting the dust on their skin. And our main Lunabotics website just now got updated with a link to yesterday's video or yesterday's live stream and a link to this current live stream. So probably the easiest way for you to advertise to friends and family that want to find the links to these live streams, just tell them nasa.gov/Lunabotics. It's very easy, nasa.gov/Lunabotics, and they'll be able to find it right there, really big and bold at the top of that screen or at the top of that website. Our judges, as you can see, are preparing the field, the 2 arenas. We have labeled Arena A as the near arena or the rightmost arena, and we've labeled Arena B as the leftmost arena or the far arena on these camera views. Both arenas are essentially set up the same, where they have a starting area on the far right, which acts like the surface of the moon that these robots were just dropped off at from their lander. And then on the opposite end of the arena, the far left side, beyond the orange lines, is going to be the area where the robots are allowed to excavate or dig. So starting area on the right and the excavation area on the left. Of course, it depends which camera you're looking at. Let's focus on the overhead camera, which is in the upper left of the screen right now. So the far right is where the robots start, and the far left is where the robots are allowed to dig. In between the starting area and the digging area, though, there are some obstacles. There are some large rocks that you can see in this overhead view. There are some craters that some of our robots may or may not be able to drive through. And there's actually a hill or a berm towards the left side of both of our arenas, Arena A and Arena B. And so these robots don't just have the simple task of, just digging and dumping their haul on the lander. They have to figure out how to even what's the best way to get to the excavation area. Am I able to drive over this rock, or do I need to drive around this rock? Some of our robots that are competing today are going to have automated software that will help them decide whether there are rocks or craters in front of them and how to get around those rocks and craters. Some of the robots you'll see compete today are going to be just completely manually stick-driven by the students. However, the students who are driving these robots are not in the same room, and they don't have these amazing camera views that we have. The students that are driving their robots are limited to onboard cameras that they have designed onto their robot, or they can optionally take a little bit of a penalty, a little bit of a score hit, and use a NASA-provided camera that acts like a lander camera that gives them essentially an overhead view of the entire field. So we can see the judges are going to be the ones that have the full face helmets on. And then when the students come into the arena, they're not going to have the full face helmets. They're going to just have the N95 masks. in order to keep them from inhaling any dust that might be lingering in the air in between runs. The reason the judges have the full head-mounted helmets on is because those judges are in that arena all day long, and the N95 mask is a temporary solution, but not quite good enough quality to keep the dust from being inhaled if it were tried to be used all day long in this competition. So don't go anywhere. Stand by, because it looks like our students are getting prepared to bring their robots into the arena momentarily. And those first two teams are going to be Purdue and New Mexico Tech. And then looking ahead, after that, we're going to have Arkansas and possibly another team, or possibly they'll run by themselves. So don't go anywhere. You're watching NASA's Lunabotics robotic mining competition here at the Kennedy Space Center Visitor Complex in sunny Florida. You're watching NASA's Lunabotics competition here at the Kennedy Space Center Visitor Complex in Florida. And I was just in the robo pits, which you're seeing on the screen right now, and asked the pit boss earlier what happened to our original first two teams. Rochester and Akron were originally scheduled to run first today, but sadly they are just not quite ready. They're still struggling, working on some issues, and so those two teams, Rochester and Akron, have stepped aside and let the other teams go in front of them, and so we're still hopeful that those two teams, Rochester and Akron, are able to solve their issues and compete later on today. So stay tuned because the schedule is changing in real time, and we'll try and keep you updated as we learn new information regarding the schedule. So right now we are expecting Purdue and New Mexico Tech to bring their robots into the arenas any moment now. And it looks like one of those two teams has brought their robot into the arena. So if they're heading toward the A side, that would mean that this is the Purdue team. And yes, I do recognize that robot. That is Purdue's robot. And now we can see New Mexico Tech's team bringing in their robot into the B side. Now, as the Purdue students bring their robot into the arena, we'll get a nice close-up look at their robot. Now, if you're not familiar with Purdue, which I wasn't until fairly recently, Purdue is in West Lafayette, Indiana. You might know them as the Boilermakers or the Boilers. They're also call themselves the Boilermaker Special, which is a Victorian-era locomotive. And that nickname came from the late 1800s when the Purdue football team just completely dominated the competition. And the newspapers were calling them a great big burly gang, rail splitters, blacksmiths, foundry hands, and boilermakers. And the fact that the local railroad company's main locomotive shop was not too far from campus helped fuel and solidify that Boilermaker nickname. Now, Purdue's robot has 4-wheel skid steer or tank steer chassis, and it has a bucket ladder system that rotates down and plunges down beneath the surface. And those buckets that are gold colored rotate around and they dump the material into a dump bed that has a mesh bottom that allows the small particles through. And we're getting a little bit of a camera cleaning right there. Thank you, Drew. Drew, one of our judges and one of my SwampWorks fellow coworkers. Other coworkers I notice in the arena today are AJ, and I see Joe. And now we're seeing New Mexico Tech bringing their robot into the arena on the B side. Now their robot uses tracks instead of wheels. And so hopefully we'll be able to see whether one of these two design choices works better than the other. Does a rubber tracked vehicle move and locomote on this sort of slippery, sort of fluffy, yet hard underneath surface? It's a really unique material to drive on and to dig in. Now, I'm fairly certain this New Mexico Institute of Mining and Technology team, or New Mexico Tech, as they're commonly known, is a rookie team. I do not believe that this school has ever competed in Lunabotics. Caveat being, sometimes I say things that are wrong. So we're happy to be corrected in the chat, though. So don't be shy to give us information or gentle corrections in the live chat, and we'll try and keep an eye on the chat. But another caveat is that we could miss the chat, so we apologize if we miss something important in the chat. But we want to encourage you to use the chat as a community to communicate with each other, information, and to ask questions and answer questions in the chat. And we'll try and monitor the chat also, and try to answer questions too as we're available to do that. The New Mexico Tech team, they are the miners, or the Miner 49ers. Originally, New Mexico Tech was the New Mexico School of Mines. And when I was looking up New Mexico Tech on Wikipedia the other day, something really interesting came up. It turns out that in 2003, the university actually bought the town of Playas, New Mexico, along with the surrounding 1,200 acres, in order to use as a research and training facility for the university's first responders and counterterrorism programs. So when the school purchased the town of Playas, New Mexico, that town was essentially an unoccupied ghost town, because it was formerly a company town that was developed in the 70s specifically for employees of a specific copper smelting company. And during its heyday, that copper smelting company, the town of of Plius had a population of over 1,000 residents, along with nearly 300 homes, a post office, a grocery store, a medical clinic, a bowling alley, a restaurant, a rodeo arena, horse stables, a fitness center, a shooting range, an airstrip, and a swimming pool. And now that town is a ghost town and used for research purposes. That is just an amazing fun fact about New Mexico Institute of Mining and Technology. Again, we have New Mexico Tech on the left of the screen and Purdue on the right side of the screen. And if you're familiar with Purdue at all, you know that they have an amazing history of just some amazing, highly notable alumni. The most notable of which is Neil Armstrong, Apollo astronaut and first on the moon, is a Purdue alum. Also, Gene Cernan, who was a Gemini and Apollo astronaut, and the last person on the moon was also an alumni. And also Roger Chaffee and Gus Grissom, who were both Apollo astronauts. And that's not all, because their list of shuttle astronauts is so long. Let's see how quickly I can get through this list of shuttle astronauts that are Purdue University alumni. We've got John Blaha, Roy Bridges, Mark Brown, John Casper, Richard Covey, Andrew Fustel, Guy Gardner, Greg Harbaugh, Mike McCulley, Laurel O'Hara, Gary Payton, Mark Polanski, Jerry Ross, Lauren Shriver, Scott Tingle, Janice Voss, Charles Walker, Mary Weber, Donald Williams, and David Wolf. That is an amazing list of alumni from one institution. So Purdue, there's obviously, I'm not a scientist, but there's obviously something in the water in West Lafayette, Indiana, in order to produce that many astronauts over the years. So hats off to Purdue. And it looks like we are waiting for something to happen. I'm looking at my screen here to see what it's telling me. We're probably waiting for an arena, something to be ready to go, and then the students will be given a specific amount of time, which I believe is 5 minutes, in order to activate, test, set up their robots. And so we'll see the activity and the body language change when that 5-minute timer actually kicks off. And looking ahead, my schedule still says that after Purdue and New Mexico Tech have their run, we're going to have the University of Arkansas running, and nobody in the other arena. And I will let you know if I see anything different pop up on my schedule. So looking even beyond that, let's assume that Arkansas runs all by themselves. That would essentially be the end of our attempt to give every team that's here Monday and Tuesday their first official competition attempt, aside from those two teams earlier that stepped aside because they weren't ready, Rochester and Akron. And so what I suspect will pop up on my schedule after that point, and I don't know if we're going to take a break or if we're just going to go right into this next segment, but the next segment will be giving all of our teams that are here Monday and Tuesday their official second attempt, and we're going to, I suspect, not take a break. I suspect we're going to go right into that mode of running these robots as quickly as we can in order to try and get through all of these teams, to get through their second attempt of all of these teams before we run out of time and are not allowed to. We're not allowed to run this competition too late in the evening. So we definitely have to try and get through all of these teams as quickly as we can. And I'll be updating verbally on this live stream as the schedule changes. And if we can, we'll try and also put it into the text of this live stream, what we know schedule-wise. So don't go anywhere, because in just the next few minutes, I think we're going to see Purdue on the right and New Mexico Tech on the left perform their first runs of Lunabotics 2022. So the 5-minute setup time for these two teams has started, and that's when you saw the the teams activate their robots, and you saw the New Mexico Tech team on the left attach some black and white barcodes to the front of their lander. That's basically that mesh screen, which is rectangular in shape, is basically simulating the lander that the robot will be needing to come back to with its load of rocks, and it will need to dump the rocks onto that mesh screen, that sieve. And that black and white barcode it implies that this New Mexico Tech robot is going to have some automation, if not be completely and fully automated during its run. Those black and white barcodes are used to calculate using trigonometry to calculate where the robot is in 3D space using simply a black and white camera. So it doesn't even require a high resolution camera or a high frame rate camera. You can get fairly high resolution position accuracy data using a simple webcam and a black and white barcode like the one seen on the New Mexico Tech side of the arena. When the Purdue students activated their robot, it appeared that the right side wheels were active, and so the robot actually kind of spun around in place. So I suspect the students back in the control room have been troubleshooting the problem and have hopefully fixed it. And now the student and the arena judge have moved the robot back into its starting position. Both of these robots are facing to the left on the screen. The front of the robots are kind of the pointy end in both cases. And so the front of the robots are right now facing left. So both of these robots are going to have to either spin in place or back up and turn. And we will see in just a few minutes how these robots get themselves from the starting position over to the digging area. As the students exit the arena judges are going to go through their last-minute checklists and make sure all the judges are ready, make sure the students are ready in the control room. The judges in the arena today appear to be coworkers of mine, Drew and AJ and Joe and Evan. But what you're seeing on the screen is a very, very small percentage of the probably 100 or more people that work at the Kennedy Space Center and have volunteered their time this week to support this competition by working here this week instead of working at their desks. And so we want to thank all of the volunteer workers from Kennedy Space Center. And we've actually, I should mention that we actually have our judging team actually came from all over the country. We've got folks from other NASA centers. We've got folks from Caterpillar. We've got folks from all over the country that have been recruited by our head judge, Rob Mueller, to help us put on this event and to help us judge this event. And we could not put on this event without so many volunteers that have been able to help to come to Florida and help us run this event. So thanks to everyone on camera and behind the scenes that you'll never see on camera, but this event would not be able to happen without their help. Just like that, this run has started for these two teams. the New Mexico Tech robot, right out of the gates, backed up and is turning. And we're going to presume that this robot is autonomous, although we don't actually have visibility into whether these robots are autonomous or are being manually controlled. What we can do is kind of watch them closely and kind of surmise based on the way that the robots act. Um, if I was if I was manually drive sticking this robot, I would just be full throttle right now, straight down toward the left side of the screen, right? And I bet you would too, viewer. So the fact that this robot is being very slow and very careful and very gentle, and it almost looked like it scanned from left to right a little bit ago. So I'm assuming that the New Mexico Tech robot at the top of the screen is fully autonomous right now. And the reason that these students might choose to run in fully autonomous mode is that they get a lot of bonus points if they're able to perform their entire run. Well, let me back up. They get a certain amount of bonus points if they're able to um, just do their digging autonomously, and they get a certain amount more autonomous points if they're able to traverse the obstacle course and dig autonomously, and they get even more points um, if they're able to do the entire run, start to finish, multiple cycles, multiple loops of back and forth. Um, this autonomous um, tracked vehicle is looking really smooth and really good. It appears to have been able to see both of those rocks and to be able to navigate between them. And if it had gone straight after going through those rocks, it would have had to climb over that berm or that hill, which is just to the right of where the robot is now. And so it apparently saw that berm and decided to steer left to go around that berm. And so, will the robot recognize when it has gotten itself to the digging area, and will it start digging autonomously? Meanwhile, the Purdue robot at the bottom of the screen um, has not quite started moving yet for some reason. So we'll have to keep an eye on that Purdue robot. In this view, you can see the digging side of the arena from that perspective, and the New Mexico Tech robot is very close. There's one last rock there that it looks like it got past. If you see on the left of the robot, or the robot's right, but on the left of the screen, there's a dip or a crater that the judges have created in the at the very end of the obstacle area. And so it looks like this New Mexico Tech robot has been able to get itself positioned between that rock and between that crater. And it looks like the back end of the robot may have slid a little bit into the crater. Hopefully it can get itself out of there. I can see the one of the drive belts spinning, and I would hate it if they got this far and couldn't get out. My suspicion is here's what the teammates are having to think about. It's possible that if those students got out of autonomous mode and just started stick driving this robot, that they would be able to get it out of this little hole that they're in. But they're probably holding back and just waiting and hoping and crossing their fingers and hoping that this robot will be able to get itself autonomously out of where it's at. Because if they can keep this robot in fully autonomous mode for the entire 15-minute run, they will get so many bonus points. It will be worth their patience. On the right side of the screen, looks like the Purdue robot is still not left the starting area, nor have I noticed it moving at all so far, sadly. So this New Mexico Tech robot, technically right now, if they were to dig in that spot, I'm fairly certain that that is a legal place to dig. It would be perfectly legal for them to dig there because their digging implement is over the line. I do not believe their wheels have to be over the line, but we'll check the rules and find out what the rules say for sure. Of course, that being said, if the robot is programmed to not dig until it is a certain distance beyond the line, then the autonomy software may kind of be in a place where it can't progress any further. So if that is the case, and I'm just throwing out some assumptions and some probablys and some maybes here. I don't know anything about the design of this robot or the design of their autonomy software. But if those students are in that predicament, um, that's going to be a tough decision for them. Um, should they be more patient and wait and see if the robot gets itself moving past where it's sitting right now, or should they give up on the autonomy points and just grab the stick and manually run from here on out? We're 7 minutes in to a 15-minute run for both of these teams. This is the first of two competition runs for both of these teams. Purdue in the background hasn't moved since the start, and New Mexico Tech in the foreground appears to have gotten to this digging spot or this near digging spot autonomously, as far as I can tell. All right, looks like the 15-minute timer has run out on this run, which is really sad to see for both of these teams. But the good news is this was run one of two runs, and both of these teams are able to go back into the pits and fix whatever the issue was that they encountered and come back for a second run. Really exciting to see New Mexico Tech, a rookie team, get so far. They got out of the starting block. They got through the obstacle course, which honestly, this obstacle course is tough. It has rocks, craters, and a berm, a hill. And it looks like the robot really technically did cross its digging implement across the dig area into the digging area zone. So that is a large percentage of the task that these robots need to perform. The only thing remaining for that New Mexico Tech robot would be to actually dig down beneath the top layer of crushed volcanic rock to get to the gravel that we've hid beneath, pull up that gravel, as much gravel as it can hold, and then haul that gravel all the way back through the obstacle course and deposit or dump the gravel at the lander, where the judges would then pull the gravel off of that sieve, that mesh, and weigh it by hand. Which reminds me, for everyone who watched yesterday and is interested in what the scores are, well, only one of our teams yesterday was able to successfully return the gravel, return the rocks to the lander yesterday, and that was Michigan Tech University, and they were able to deliver 0.3 kilograms of rocks to the lander. So a lot of robots yesterday. A lot of teams had various issues, and so their job then becomes to troubleshoot those issues, try and fix those issues, and come back for a strong second run today. What I have next on the schedule is I have University of Arkansas is going to run next, and it will be just them. We will not have a robot in the other arena. So stand by, don't go anywhere. As we watch the judges reset the arenas and get the arenas all cleaned up and prepared for Arkansas's run, which will start in just a few minutes. So don't go anywhere and keep watching Lunabotics 22 live streaming from the Kennedy Space Center Visitor Center here in Central Florida. we're seeing on the screen is the University of Arkansas team getting their robot loaded into our Artemis Arena. So they'll be running, and they'll be the final team in our first round of runs. And then looking ahead, what's going to happen is we'll take a short break while the judges prepare the arena for all of the students' second run. And I'm not 100% sure, but I wouldn't be surprised if the judges actually change the obstacle course for the second run so that the robots and the teams get a slightly different positioning of the rocks and craters and so forth. And so as soon as the judges get the arena ready for the second round of runs for all these teams, I'm told that Michigan Tech and Milwaukee School of Engineering are going to go first. And then we'll have Colorado State and the United States Military Academy. And then we'll have University of North Carolina at Charlotte and Saginaw Valley State University. So we're looking at the University of Arkansas team getting their robot ready to run. It's their first run of the competition. And their robot looks to be another four-wheeled skid steer or tank steer robot, most likely four-wheel drive. And the towards the bottom of the screen, it looks like a digging bucket that has holes in the bottom of it to let the fine powder fall through and leave just the gravel, the rocks remain. And it's not obvious to me that this robot has another spot on board to deposit those rocks. So I'm assuming that the robot will get a shovelful and then drive back and dump that shovelful and then go back and forth, kind of like a bobcat, like a skid steer bobcat that has a bucket in the front. This is looks a lot like that sort of design. Although that bucket, I may be completely wrong. That bucket does not appear like it could reach the ground unless I'm missing something fundamental. Let's go to this angle. We're able to see more. There's definitely there's a rotating bucket drum in the middle, a thin in width. It's only about maybe 2 inches wide. Thin rotating. It's black colored on the screen right now. And so in the middle of the robot, it looks like there's a rotating, spinning bucket drum that has openings or teeth or buckets on it that when they spin around, they will capture the crushed rock. And I'm assuming that can be lowered down below the surface. And so once they've dug down deep enough to get, also there's holes in that rotating bucket drum. So hopefully after they've dug down deep enough and they can lift that bucket, hopefully they've captured some rocks and they can lift that rotating bucket drum up out of the hole that it just dug, maybe continue rotating it so that the fine dust will fall out of those holes, and then they'll only have the rocks remaining. And then I presume that somehow they'll have to lift that thing up high, that digger, and somehow deposit those rocks into the holder, the bucket, for lack of a better term, that you see on the right, which is a shiny metal color. And then presumably that dump bed can lift up and rotate in order to dump those rocks. Of course, I could be completely wrong about how this robot's designed, but we'll see hopefully in the next few minutes when this competition run starts for the University of Arkansas. They have just a minute or so remaining left in their setup time in order to check out the robot and make sure everything is communicating properly, everything can be commanded and monitored the way that it needs to be. And it's kind of interesting. It almost looks like they've put red tape on one of their wheels, and that may be because their wheel treads were too grippy, and so they wanted to settle out some of that grippiness by smoothing out some of their wheels. All right, looks like the teams are done setting up their robots, and the judges are getting ready to put the final touches on the arena before we start this run. Again, this is University of Arkansas. After University of Arkansas has their 15-minute run, we will the judges will take a break to reset the arena for all of the second runs, and then the teams that we have on the schedule right now to start their second runs after the arena's been changed around and prepared for the second runs. Right now we have Michigan Tech and Milwaukee School of Engineering and then Colorado State University and the United States Military Academy, or West Point. Then we have the University of North Carolina at Charlotte and Saginaw Valley State University. And then all the other teams will follow. But I don't want to waste everybody's time by reading off more than the first few scheduled runs, because this schedule is so fluid, and things are changing so drastically. So stay tuned, don't go anywhere. Momentarily, we should see this robot from the University of Arkansas start its first of two 15-minute runs in our Artemis Arena. All right, we just saw some movement from this Arkansas robot. It wasn't the wheel movement, it was a lifting of their dump bed, is what it looked like to me. So their 15-minute competition run, number one of two, has started. And so let's keep a close eye on this robot and see how it handles getting out of the starting position and through the obstacle course. It looks like these Arkansas students are able to control their dump bed lifting and lowering. So hopefully they'll be able to figure out whatever issues they might be having controlling the wheels of this robot and get this thing moving out of its starting position. We hate to see this happen, but we have not been able to see this Arkansas robot move from its starting position, and it looks like the students are coming back in. So it looks like they may have a problem that's bad enough that they have decided to go ahead and call it early and not go through the entire 15-minute run. So sad that this happened to the Arkansas team, but since this was their first run of two, we're gonna cross our fingers that that they know what's wrong. They'll be able to quickly go back and fix it and come back for a solid second run later on today. Now, looking ahead, we're going to give the arena judges some time to change the obstacle course, is what I'm presuming they're going to do between all of the teams run one and run two. And as soon as the judges tell us that the arenas are ready for all of the round twos, we should see Michigan Tech and Milwaukee School of Engineering coming up first. Then we'll see Colorado State University and the United States Military Academy. And then after that, we should see the University of North Carolina at Charlotte and Saginaw Valley. And then the rest of the field, which includes Iowa State, California State Long Beach, NYU Tandon, the University of Alabama, Miami-Dade College, Florida Tech, University of Akron, University of Utah, New Mexico Tech, University of Rochester, University of Arkansas, and Purdue. Hopefully we will get to see all of those teams compete in these arenas later on today. So don't go anywhere. Things are about to get interesting as teams start to compete, start to go in the arenas for their second round of competition, second runs for these teams here at the NASA Lunabotics 2022 edition, streaming to you live yesterday, today, and Thursday and Friday, live from the Kennedy Space Center Visitor Complex here in sunny Florida. Don't go anywhere. We'll be back soon. This year marks 60 years of Kennedy Space Center supporting science, technology, and human spaceflight. Over those last 6 decades, NASA has continued to push the boundaries of science and exploration, sending science missions to the deep recesses of space to learn more about our universe, creating orbiting space stations that have led to more than 20 years of continued human presence in space, and landing investigative rovers on our neighboring planet in preparation for the future of exploration. Today, we are dreaming bigger and going further than we ever have before, and we are taking America with us.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
You're watching NASA's Lunabotics competition, streaming live from the Kennedy Space Center Visitor Complex here in Central Florida. And I'm walking through the robo-pits. These students are getting their robots ready for the second of their 2 runs that they're getting in the competition this week. And I'm seeing a mixture of attitudes. I see some teams that are calm, cool, and collective, ready to go. I see some teams that appear to be in a mild panic situation, trying to get some things fixed, or maybe working for the very first time. And it's there's definitely a lot of energy, good energy and bad energy. But even some of these panicky teams, they may not end up running until towards the end of the day, and so that means they still have several hours to get whatever their problem is happening fixed and get their robots into a working order. So keep watching our live stream, and we will go back to our arena runs for these teams in just a little bit. But in the meantime, let's just keep an eye on the RoboPits and watch the teams prepare their robots for the second of 2 run opportunities, 2 scored competition run opportunities that these students are getting this week. It looks like our judges have prepared the arenas for the second run of the robots. And so what we should be seeing, if my schedule is correct, is Michigan Tech and Milwaukee School of Engineering loading their robots into the arena for their second and final scored run competition runs in the arenas. And what I'm noticing is that the robots are starting out in a slightly different orientation. For the first run, it seemed like all the robots were facing to the left. And for the second run, it appears that all the robots are going to be facing towards the digging area, or to the lower left of the screen as you see them right now. My computer hasn't updated, but if the paper schedule that I have in front of me is correct, then we should be seeing Michigan Tech on the A side, which is on the right side of the screen, and we should be seeing Milwaukee School of Engineering on the B side, which is the far or left side of the screen as you see them right now. Make sure you tell your friends and family and coworkers to watch this live stream with us today. You can probably the easiest way to advertise either to friends or family or on your social media accounts is to post a link to our main Lunabotics website, which is nasa.gov/Lunabotics. It's easy to remember. It's easy to type. It's all lowercase. It's just nasa.gov/Lunabotics. That is our main event website. It contains all of our rules and our history of the competition. But most importantly for this week, at the very top of our nasa.gov/Lunabotics is a post or a banner that has links to the current live stream, and actually there's also a link to yesterday's live stream if by chance someone out there in the world would like to go ahead and rewatch that one. Wish I could tell the viewers that there was a website that they could go to see live stats for each run that occurs live, but we don't have a system in place that updates a web page, a public web page, live with statistics. I will tell you that on my screen, which has given me live statistics here in the building in house, we've only had one team so far bring and deposit any gravel back at the lander, and that was Michigan Tech University. In their first run, they were able to bring back and deposit 0.3 kilograms of gravel. And so it's going to be really exciting to see the second run from all of these teams, Michigan Tech and all of the others, because presumably they have all learned what went wrong yesterday. They've all learned, have lessons learned and implemented their lessons learned onto their robots or onto their laptops or wherever the problem occurred. And I'm hopeful that this for the rest of today, where we will see the second and final runs for all of these teams that are competing here Monday and Tuesday. I'm hopeful that we will see lots of robots bring and deposit lots of gravel, lots of rocks onto the landers. And then make sure you come back Tuesday and Thursday, because we will basically do this all over again with a whole new set of teams, because we've split our competition this year into two groups. So what you're seeing on the screen is Michigan Tech University on the right and Milwaukee School of Engineering on the left. They are in the middle of their activation time, their robot activation and checkout time, where the students in the arena are communicating with their fellow teammates in the control center, which is in a completely different room, completely walled off from the arena. The students in the control room cannot see, hear, smell, taste. They have no visibility into the robots other than the sensors that are on board the robots. If they put a camera on their robot and send that camera signal over to their router, then they'll be able to see that camera signal back at their control station. The only data that NASA will be providing teams during their run is an optional overhead camera view that if teams decide not to use that overhead camera view, they will basically get a point advantage over teams that choose to use the camera view. That will basically give them a slight disadvantage. And the logic behind that is that if a robot is able to minimize bandwidth usage and do everything it needs to do self-contained internally, then that is a benefit, that is an advantage. And so that's how we're handing out that advantage. So from the body language that I saw, and the fact that the robot moved, it appears to me that the Michigan Tech robot on the right is ready to go for its second official competition run. And meanwhile, the Milwaukee team is spending the last couple minutes of their setup time possibly troubleshooting a problem, or maybe they're just being very thorough and making sure every little last thing is working before they exit the arena. I want to thank the 100 folks who are watching this live stream right now. And if you have friends or family, or just have a social media account that you want to share our link on, feel free to do that. And tell everyone who you think might be interested in watching these robots run about our live stream so that they can enjoy it along with you. Right, it looks like all the students from both teams have left the arena, and so that means that this second run of two, or final run for both of these teams, is going to be starting momentarily. So don't go anywhere. We're off. So what we're seeing on the A side, which is the bottom of the screen, That's Michigan Tech University. Looks like the robot went forward for a bit and then went backward. So trying to get its bearings maybe. We can see in this view that the robot at the top of the screen, which is steering, we can see one of their wheels. Oh, now we're seeing some others of their wheels moving. And at the bottom of the screen, that's our Michigan Tech University that we were just mentioning earlier had actually some good success yesterday with getting to the digging area, digging really deep, and returning some rocks, some gravel to the lander. But in their second run, it appears that Michigan Tech's robot might be having some mobility issues. We don't have a good camera view that can see this robot from the other side. There may be some sort of problem with the other side of the robot. I'm not really sure what is keeping this robot from going further than it's already gone. Well, look at that. It just took off. It may be having some steering issues, because what it really needs to do is go to the left of the direction or down towards the bottom of the screen. So I wonder if one of the motors is not working, or I wonder if one of the wheels has disconnected from its drive shaft. There's a number of mechanical issues that could have occurred that could cause this sort of behavior. There's also software issues possible. You know, as a software engineer, I'm fully aware and have lots of experience with software bugs. So sometimes software issues crop up in operation that never cropped up during testing, because the operational environment is always there's always some subtle difference between the operational environment than the testing environment. And as engineers, we try our hardest to make the testing environment match the operational environment as closely as possible. For example, in the space program, if we are going to send a device, a satellite or a payload or a rover, whatever that thing is that we're sending into outer space, we want to test it before we put it on a rocket, and we want to test it in an environment that simulates or emulates the environment that it'll be in. So let's say an example would be a satellite that is in low Earth orbit. It sees very cold temperatures when it's not looking at the sun, and it sees, hot temperatures when it's looking at the sun. So we have ovens on the ground that can simulate hot temperatures. We have freezers or cryogenic coolers on the ground that can simulate cold temperatures. But the environment is more than just strange temperatures. Orbiting the Earth, a satellite sees 0G for hours, days, weeks, months, years, depending on how long the mission is, Well, how do we simulate zero G on the ground? That's a lot trickier than simulating a temperature, but we do have several ways that we can try our darndest to simulate zero G here on the ground. We have drop towers, which are tall towers, tall facilities, tall buildings, where we can literally drop a payload or drop an experiment from a certain height and let it fall through, many stories, and then land in an airbag. And so in a facility like that, your experiment can get a few seconds, maybe 2, maybe 3, maybe 5, 6 seconds worth of free fall, which is a very good emulation of zero G. Well, what if that's not enough time to test your experiment? What if you need longer than that? Well, in that case, we have zero G airplanes that can fly in parabolic patterns where they bring the nose of the airplane up and they climb to a certain altitude, and then they start to nose the airplane down ever so gently in order to create a free floating experience inside the cabin. And in an airplane like that, we can get 20 or 30 seconds of zero G or free fall in every single parabola, and we can fly multiple. We can fly tens or 20 or 30 parabolas in a day, and so you can end up getting a lot of cumulative zero G flight time on experiments. And if you needed more zero G time than that, then maybe you can get your experiment sent up to the International Space Station, where it can get months and months and months, possibly even years worth of zero G time before it is sent on its final mission. Checking back in on our robots, we've actually seen some movement from both robots. The Michigan Tech robot, which is the lower one on the screen, you can see its tire tracks. It was able to drive forward, but probably not in the direction that it wanted to drive. And it also raised up its digging system, which is a bucket ladder system on like a conveyor belt. Well, it's actually driven by chains. And then the robot at the top of your screen, Milwaukee School of Engineering, we did see the wheels move a little bit earlier, but the robot didn't seem to make very much progress on the surface. But we did see them also deploy their bucket ladder digging system. But sadly, neither one of these robots have been able to make it to the digging area in order to start digging, and they have about 6 minutes left in their 15-minute run. Now we see some digging going on from this Michigan Tech robot. But since the robot is not digging on the left-hand side of the screen, which is the legal digging area, this is actually not going to get them any points. I suspect the team I suspect the students are just um, making the most out of a bad situation where they don't appear to be able to get their robot over to the digging area. And so before their time runs out in the Artemis Arena, which is full of crushed volcanic rock, tons and tons and tons of crushed volcanic rock, they're just taking this opportunity to get some runtime on their digger, and maybe they'll get some data that will be useful for tweaking their robot design. Looks like we have about just a couple minutes left in this round for these two teams. And then looking ahead, we should see Colorado State University come in next, along with West Point, the United States Military Academy. And then after that, we should see a run from University of North Carolina, Charlotte, and Saginaw Valley State University. Now you can see the dump bed working on the Michigan Tech robot, and the judges are there to kind of start getting the robot cleared of all the fine dust particles that can get all over these robots. Part of the unique challenge with this competition is the uniqueness of the crushed volcanic rock that they have to operate in. These small crushed rock particles can really do a number on your robot, especially if your robot has any soft parts. The particles are very jagged, very very sharp, and they can do damage to soft seals in robots or in spacesuits, as we found out during the Apollo missions, that the lunar dust really did a number on the seals in the astronaut spacesuits. But beside that, the particle size is very small. These fine particles can work their way through seals. They can work their way through any gap that that they can find, and so they can really get in the works and get into places that you really don't want this destructive dust. Aside from just dust being an issue for lunar robots, the actual surface, which is covered with this fine dust, is a unique entity of itself. Down beneath the surface, these fine dust particles become packed. They become compacted, but the top several inches remain a light and fluffy, dusty powder. And so, if you go back and look at Apollo films of any videos that were taken during the Apollo surface operations, you'll see how the top layer of dust gets disturbed fairly easily and becomes lifted up off the surface. And so we have to consider these properties of this dust when designing our lunar robots. We have to design a robot that can move across the surface and handle this light, fluffy powder on top, but also handle the more compact material that is just a little bit below the top surface. And it's not an easy task. I would bet that most of these robots would be able to. You'd be able to take them to the beach and drive them around on the beach sand, and they would be able to perform all day long in that environment. And as soon as you bring them into our Artemis Arena here at the Kennedy Space Center Visitors Complex, where they have to deal with this very unique fine dusty powder on top and a very compact and very resistive powder beneath that, it's totally not this it is not the same as beach sand, and it acts completely different. And you really have to take special design considerations in order to handle this unique environment. So as we watch the judges and students prepare to remove the Milwaukee School and Michigan Tech robots from the arena, we should see coming up in the next few minutes. Of course, the judges will need to take a few minutes to reset the arena for the next two competitors, but those next two competitors are going to be Colorado State University and West Point, the United States Military Academy. So stay tuned for our next two competitors and don't go anywhere because we are live streaming the entire 4 days worth of NASA Lunabotics 2022 competition here live from the Kennedy Space Center Visitor Complex in Florida. In case anyone is just joining us, you are watching NASA's Lunabotics Collegiate Robotic Mining Competition, and we are here at the Kennedy Space Center Visitor Complex in Florida, right outside the NASA gates. And we have brought nearly 40 teams of college students from around the country here this week. We've split them into two groups. About half of them are performing yesterday and today, competing in order to see who can traverse across an obstacle course, dig way down beneath the surface in order to pull up the rocks that we've hidden beneath the surface and bring those rocks all the way back to the starting point and deposit them at the lander. And the other half of our group is going to, we're taking a break on Wednesday, at least taking a break from our live stream in order to swap out our groups of student teams. And on Thursday and Friday, we will be live streaming again and running the second group of our collegiate teams that have come here to compete this year. Now, this Lunabotics event that you're watching our live stream from is only one of several NASA Artemis challenges. So find a challenge that is in line with your skill set and your interests.
NASA's Artemis mission will land the first woman and the first person of color on the moon.
And today's students are the Artemis generation.
If you're a student, you can design and build technologies that support the Artemis mission with NASA's Artemis Student Challenges.
No matter your background or experience,
you're invited to choose a challenge that interests you, whether it's
rockets,
robots,
tools,
software, vehicles,
or other technologies. There's an exciting challenge for you.
So find a mentor and build a team of students.
Review the rules and requirements.
And bring your ideas
to life with NASA's Artemis Student Challenges.
Visit stem.nasa.gov/Artemis and see how you can join one of NASA's mission-related student challenges.
You are watching NASA's Lunabotics Collegiate Robotic Mining Competition. And what we've got on the screen right now, our next two teams have entered the arena. They've set their robots into the arena. And the teams are Colorado State University on the right and West Point, United States Military Academy on the left. So both of these teams are preparing to activate their robots and verify that they're working before before their runs will start. You can see the students talking on the radios. They're actually talking to their fellow students, their fellow teammates in another room down the hall, where those students in that other room down the hall, they're in the control room getting ready to monitor and control their robot from a remote location, which sort of simulates controlling these robots from Earth that are actually operating on the moon. I noticed in the chat there's a question about the starting orientation of the robots. I'm assuming this, I haven't verified this with any of the judges, but what I noticed is all of the round one runs all had the robots facing to the left. And what I've noticed that so far, all of the round two runs have started with the robots facing towards the digging area. So I suspect that the judges have made that decision offline, and they've decided that those are the two positions that they're going to start all the robots in. Position one for run one and position two for run two. Again, this is all a presumption, and I haven't verified that with the judges. But that's what it's looked like. That's what it looks like is happening. All of the run two robots appear to be starting out in the same location, but a 90-degree shift in orientation of pointing angle from all of the run ones. So I guess what I'm pointing out is that the students don't get to choose the location nor the orientation of their robot. It's the judges that tell the students where to position and how to orient their robots. But from what I can tell, run one was all the same, and so far run two have all been the same. Versus in prior years, where some students may be aware that in prior years, the teams actually had to roll a dice, like literally roll a dice before they went into the arena, which told them their starting location and starting orientation. But it appears to me that that we're not randomizing or rolling the dice this year. So not being able to listen in on the students communicating between the arena and the control room. It would appear, though, that the West Point students are ready to go, and that the Colorado State University students, although they're being removed from the arena now, they were definitely conversing over the radio right up until the last second. So hopefully that wasn't a panic situation. Hopefully everything is working well, and hopefully both of these robots are fully working, fully operational, and ready to get in a good scoring run here in their second attempt. While we wait for this run to start for these two teams, Colorado State on the right and West Point on the left, the teams that should be coming up after this run should be North Carolina Charlotte and Saginaw Valley State University. And after that, we're going to have probably a full hour break for lunch for all of these teams, all of these volunteers, all of the staff. They have been working hard, and so they deserve to sit down, put their feet up, have a nice relaxing lunch before we start up again this afternoon. We will continue our live stream, though. We're not going to halt the live stream. If we do, we'll end up with another YouTube URL that we'll have to start advertising. So we're gonna continue this live stream through the lunch break, and probably spend a lot of time looking at the RoboPits, I suspect. So again, we've got this run, and then North Carolina, Charlotte, and Saginaw Valley after this one, and then a lunch break. And if the paper schedule holds that I was given earlier, after lunch we'll see Iowa State, California State, Long Beach, NYU Tandon, Alabama, Miami-Dade, Florida Tech, Akron, Utah, New Mexico Tech, Rochester, Arkansas, and Purdue. Possibly in that order, but again, our schedule is highly fluid. So please stay tuned for up-to-date information. As we wait for this run to start, I want to give another shout out to my coworkers who are on the screen right now, SwampWorks employees who do robotic research, technology development, ISRU, living off the land, technology development for NASA as their day job. And they've basically volunteered to help us out this week. And my coworkers I see that are full-time judges, they probably have the hardest job. We've got Drew, we've got Joe, we've got Evan, and we've got AJ. And these guys probably work the hardest of all the volunteers and staff here this week. But that's not to say that everyone else has an easy job. All of our staff, all of our volunteers, they're running around. They're working very hard. They're working tirelessly. They're working long hours. Sometimes they don't have a lunch break. Although I would encourage all of our volunteers to make the time to take a break. Don't wear yourselves out. And I also want to thank the nearly 120 people who are watching our live stream right now. Thanks for taking the time to watch our live stream. Don't be shy to type something into the chat. You can cheer on your favorite team. You can ask questions if something is unclear or confusing. And maybe other members of the community would be able to answer your questions, or maybe we'll be able to answer your questions directly. And feel free to share on social media this live stream so that other folks can enjoy this competition this week. So we just saw some Colorado State students come into the arena and open up a panel and do something on their robot. So hopefully now the Colorado State robot is ready to compete and give us a good second run. And we're off. The 15-minute timer has started. And the West Point robot is out of the gates. For a second there, the front left wheel was not moving. Let's hope they can get past that, because that is not fun. And the Colorado State robot, wheels haven't quite moved yet, but its digging mechanism is lifting. Looks like one of the wheels on, at least one of the wheels on the West Point robot does not appear to be moving. It's probably actually digging in and working against the robot's progression. It did appear to work initially in order to get the robot partially out of the starting block. And now we see the West Point robot at the top of the screen lowering its digging mechanism, possibly in an effort to push itself a little bit. Again, the two robots you see on the screen, West Point, United States Military Academy at the top of the screen, and Colorado State University at the bottom of the screen. Both of these robots have about 13 minutes remaining in order to get out of the starting area, get past the obstacle field, and get down to the digging area. Oh, look at Colorado State, just lunged right out of the starting block. One of the wheels, we keep seeing this quite a bit. For just a second, it looked like one of the wheels was not moving. Looks like the judge just reached in and pulled some parts off of out of the arena. I hope those parts weren't critical to the robot's operation. So in that, just there, you could see 3 of Colorado's 4 wheels were spinning. They're powerful enough that they were spinning and spewing out some dust. But the right front wheel on the Colorado State robot, to me, looks like it's maybe not working like it should. And then on the West Point robot, the front left wheel does not appear to be working like it should, but it looks like West Point is making progress regardless. Both of these robots are making progress. As a matter of fact, Colorado State's robot has made it all the way to the digging area. And this camera view shows the Colorado State robot clearly in the digging area. And so now all this team needs to do is activate their digging system and dig down. There you can see these black plastic looking digging buckets coming across. And there's some buckets that are missing. Those might have been some of the pieces that we saw earlier. Some of these. So it's possible that these digging buckets are plastic. They may be 3D printed, and it's possible that they're either coming detached or from their brackets or just completely breaking. And then on the far side of the arena, we've got West Point. Looks like they're almost across the line and almost to the digging area. And on Colorado State, you can see underneath the front of the robot, you can see some pieces, some of those digging bucket pieces that have been breaking off or falling off of their brackets. But there's a redundancy in a system like this. If if you have a bunch of buckets attached to a rotating belt, then if you lose a certain amount of them, as long as some are still active and operating, then you can still make progress. So even though we've had a little bit of a hairy time with this robot, with things falling off of it and breaking, it's still not completely done for. It's still able to dig and make progress in this event. Meanwhile, on the other side of the arena, this is actually a pretty good angle for both robots right this second, because you can see a side view of the Colorado State robot on the right, and from this angle you can see the dust and or rocks pouring into the robot's receiving basket or receiving bucket. And we can also see the West Point robot not quite across the orange line that's drawn in the sand, which designates the start of the digging area. So the West Point robot really needs to get its digging mechanism across that line in order to have a legal dig. But again, this is a four-wheel drive robot, and so all four of those wheels should really be rotating. And if you have a four-wheel drive robot and one of the wheels, um, if one of the motors has an issue, if you blow a fuse, if you have some sort of an axle attachment problem where it starts to slip and the axle is turning but the wheel is not, any of those issues can really be detrimental to the progress of these robots, because you really truly do need all four of those wheels to be operating in order to make good mobility progress across this very unforgiving crushed volcanic rock that these robots have to operate in. And this crushed volcanic rock is a very it's a very high fidelity uh, mechanical simulant. These this is very similar to the forces that these robots will feel, and the experiences that these robots would have if they were operating on the moon. One big difference is the amount of gravity on the moon is only 1/6 the amount of gravity here on Earth. So um, the robots would would be much lighter on the moon. Whether that would help them in their mobility issues or whether it would hurt them um, is a question that I am not prepared to answer. Now, the Colorado State robot on the right, although it did struggle to get down into the digging area for a little bit, and it also struggled with several of its digging buckets on its bucket ladder system breaking off and falling to the ground. Even with all those issues, it does seem to be making some good progress in collecting some of the simulated regolith. You can see every time one of those buckets comes around, well, almost every time, it dumps some of this crushed volcanic rock. And if they're deep enough, if they've gone deep enough, they'll also be dumping some gravel, some rocks that are, maybe an inch or two in diameter. Now, that's not quite the end goal for these robots. After they collect these rocks, they have to make it all the way back to the starting position, and this Colorado State robot may have issues getting back to the starting position. It's going to be heavier than it was when it started because it's got this load now. And so if it still has those mobility issues, it has to get past those. And then it also has to line itself up with the lander in order to dump properly and efficiently. If it's not lined up well, it could potentially dump some of these rocks that it might be holding back onto the ground, and that's no good because that doesn't that's not a scoring rock. So with only 4.5 minutes remaining in this 15-minute run for both of these teams, Colorado State still has some challenges ahead of it. So it's going to be interesting to see how this robot does in getting back across the obstacle course and lining itself up to the simulated lander and depositing its load onto the simulated lander. All right, it looks to me like the Colorado State robot may be getting ready to drive back to the starting position. And as it drives away from its digging spot, what I think I see is a lighter colored, almost a white colored rock or a piece of gravel, that if that is what it looks like, that is the gravel material, the rock material that's hidden below the fine crushed volcanic rock, and that's the material that is that gives these students points for bringing back and depositing onto the lander. Time is starting to get a little bit short, less than 3 minutes remaining for this Colorado State robot to get back and deposit its load onto the lander. I'm getting a little bit nervous that this robot is possibly running short on time. So let's get that digging mechanism out of the way. Meanwhile, the West Point robot appears to have been stuck in that spot for a while. Okay, it's getting exciting for Colorado State. It appears like they're maybe dragging their digging system just a little bit. See how their digging system is kind of scraping and dragging the ground. That's going to make it harder for them to get back to the lander, and might even be causing some of their wheels to not be fully touching the ground like they need to be. Less than 2 minutes remain. So West Point appears to have kind of settled in that spot and doesn't seem like they can get out. And so they've deployed their digging mechanism, probably just to test out their systems before they run out of time. Minute and a half remaining. Colorado's making their digging system vertical. Now, I should mention, it's pretty obvious from this angle that digging system is touching the ground. But the students who are controlling this robot, they don't see this particular camera view. They're seeing an overhead view that's closer to the lander. And so it's quite possible that they can't see this problem, they can't detect it, or it's also possible that they're fully aware and they're just trying their best to get that thing out of the way. It's possible that when they lowered it, they were not able to raise it back up, and so their digging system might be. Yeah, I think they're fully aware. They're actually running their digging system, possibly in an attempt to act like a, a fifth wheel, and we just saw some more pieces fly. Because so imagine if you were digging in beach sand, your pieces, your plastic pieces would probably not be breaking and flying out like that. This material that simulates lunar soil is very, very tough to dig in. It's very unforgiving. It's very tough to drive in. And sadly, neither of these teams were able to get any points on their second run, but I want to congratulate them both for the progress that they've made. And wow, Colorado State, what an exciting run for them. They they made such great progress. They made it all the way to the digging area. They did some really impressive digging, even though a lot of the pieces of their digging mechanism were being lost throughout that process. And they made a really valiant attempt at getting the robot back to the starting point, but it looks like something went wrong, and something was in the way, and they just could not make it back. So, congratulations to both of these teams just for getting as far as they have gotten. Now, as the students remove their robots and as the arena judges prepare the arena for the next two teams, those next two teams are going to be the University of North Carolina at Charlotte and Saginaw Valley State University. Those are the next two teams that are going to be competing in our arena. And then after that, we will take a lunch break. And our lunch break will, unless somebody comes in and corrects me later, we'll presume that our lunch break will be an hour long. And then after the lunch break, we will run through all the other teams, give them all their second round, and all those teams include Iowa State, California State, New York, NYU Tandon, Alabama, Miami-Dade, Florida Tech, Akron, Utah, New Mexico Tech, Rochester, Arkansas, and Purdue. These are the list of teams who are here competing in Monday and Tuesday of our Lunabotics competition. We will have a whole nother group of teams that get swapped out tomorrow, Wednesday, and we will not be live streaming tomorrow, Wednesday, but we will be live streaming Thursday and Friday. The rest of the teams that come in on Wednesday. So don't go anywhere, because if you go anywhere, you are going to miss North Carolina, Charlotte, and Saginaw Valley State University coming up soon here at NASA's Lunabotics 2022 Collegiate Robotic Mining Competition. Stay tuned. Do you want to join the NASA workforce as an intern? Hundreds of students work at NASA centers across the country. Our internships can be virtual, in person, or hybrid. Be part of the many teams working on Artemis, Lunar Gateway, and many other NASA-related projects and missions. Our fall intern schedule is currently open for applications. So go to our website and find your opportunity today. Go to intern.nasa.gov, start your profile, and begin the journey with us. Here's a quick video with more information on how to get started.
Hi, my name is Claudia Bernier.
My name is Matthew.
Mi nombre es Miguel Marcelino.
My name is Ali Hyder.
Kai Kos.
Christine.
Bashir Makea.
Carlos Catalano.
Tess Von Ruden.
My name is Sarah Adabumi, and I am a NASA intern.
Jesse Moody, and I'm a NASA intern.
Pathways Engineering intern.
I'm a NASA intern.
I'm a NASA intern at NASA Kennedy Space Center.
At Ames Research Center.
NASA Langley in Virginia.
At Goddard Space Flight Center.
OZ Department at Johnson Space Center.
Of the Human Factors Engineering team at the Marshall Space Flight Center.
My name is Tina Shermer, and I'm a Pathways intern at NASA's Glenn Research Center.
I'm Jamarius Reed, and I'm a NASA intern for the Office of STEM Engagement, working in the Aeronautics Directorate at NASA Ames Research Center.
My name is Courtney Goldman, and I'm a NASA OSIM intern at a Kennedy Space Center.
I'm currently working with the Psychophysiology Research Lab.
I study how nitrogen functions in extreme environments.
In bioinformatics for spacecraft production.
The synthesis analysis of multidimensional ozone measurements.
I supported the X-59 Quest low boom flight demonstrator project.
I decided to apply to a NASA internship because it sounded like the chance of a lifetime to work alongside the innovators and pioneers at NASA.
We get invited to lectures from astronauts, inspiring researchers, and get to hear about smaller missions that I wouldn't have known about.
And being able to work with all of the amazing people here has truly been out of this world.
I like feeling like I'm contributing to something bigger than just me.
All the different projects that they're funding or different projects that they're investing their resources in is really inspiring.
And NASA did an excellent job providing me with meaningful work and making sure that everyone on the team felt included and involved.
From daily or weekly check-ins, my mentors guided and advised me through my projects and any help that I needed.
I feel that NASA is a source of innovation and inspiration for people of all ages and backgrounds.
But you're also around people that are humble, driven, again, passionate, really coming to work, wanting to work, because they care so much about this goal, this mission.
And all NASA wants to see is that you share that passion as well.
Always remain persistent. Everything doesn't happen the moment you want it to happen. Everything happens when it's supposed to happen. So if you apply 2 or 3 times and you don't get accepted, keep trying.
We are the Artemis generation, and I am proud and so grateful to take part in getting the next man and the first woman to the moon.
NASA welcomes everyone. It welcomes you. If you're interested in NASA at all, apply online today. I did not think that I could get an internship with NASA, but I applied anyway, and so I think you should too.
NASA internships are really great opportunities. I wouldn't actually be working here if it wasn't for my NASA internship. So I highly encourage college students, every time I speak to them about engineering and about what NASA's working on, I always highly encourage college students to apply for NASA internships. I know for a lot of students, summer hasn't even started yet, or maybe it's just now starting. So thinking about the fall semester might seem a little bit early, but I do want to point out that on NASA's internship website, which is intern.nasa.gov, they are already accepting applicants and collecting applications for the fall term. And just to give you, it is early, and if you continue to check this website over the next weeks and months, you will see literally hundreds and hundreds of fall internship opportunities at NASA. And just to give you a real quick idea of what you can find, it looks like they're hiring, Ames is hiring a internship for rotocraft aeromechanics, which sounds interesting. Stennis is hiring an architectural engineer intern for construction of facilities projects. The Kennedy Space Center is hiring fall interns in the computer science area for their Spaceport Command and Control software group. Langley is hiring computer science students for a project management dashboard project. You could work at Ames on a virtual business system that they're working on. This is just the tip of the iceberg. We've got internships in aeronautical engineering, aerospace engineering, astronomy, physics, communication, and media. You could work in a media group doing communications for NASA. So definitely go to this website and check back regularly, multiple times a week. I would suggest, as over the next few weeks and months, new internship opportunities are going to pop up on this NASA internship website. We can now see in the arena that our next two robots have been placed. We have Saginaw Valley State on the left and North Carolina Charlotte on the right. Both of these teams are checking out their robots, activating them, and communicating with their fellow teammates in the control centers to verify whether any switches need to be pressed or buttons need to be pressed or any plugs need to be plugged in, or if any computers need to be rebooted, any sort of activities like that that might need to be taken care of between the robot and the control system. And so in the next few minutes, their setup time will expire, and we will see a 15-minute run. The second attempt for both of these teams will start very shortly. Again, University of North Carolina, Charlotte on the right, and Saginaw Valley State University on the left. We're going to see two different excavation designs here between these robots. The Charlotte robot on the right has a center-mounted rotating bucket drum, and it actually is multiple drums, one inside the other. And this is a design where the interior drum starts out with its receptacle or its slot or its hole facing upwards, and then the buckets or the teeth and the teeth that you can see on the screen rotate around, and they bring the dirt up, and the dirt falls through that hole. But then later, after the bucket is full, the whole thing actually lifts up, and then the receptacle or that hole actually rotates downward or towards the back of the robot in order to release the material that has been captured inside of it. The Saginaw Valley robot on the left looks like it has a bucket ladder system, like we've seen on several previous robots, that is mounted in the middle of the robot and can change its angle, and I believe it can also drop itself down below the surface of the simulated regolith. And we're off. We have seen motion from both of these robots, which is always great to see. The Charlotte robot has 6 wheels, and the Saginaw Valley robot at the top of the screen is a 4-wheel design. Now, this Charlotte robot has driven straight so far, and what I notice is directly in front of the Charlotte robot, oh, look at that. The Charlotte robot just deployed its conveyor belt that will be used to offload the regolith. Both of these robots driving straight ahead. Sadly, both of them are pointing directly at this berm, this hill that the judges have created in the arena. And so now we see the Charlotte robot basically setting up for a 3-point turn in order to change its pointing direction in order to drive around this berm. Now, the thing the Charlotte robot needs to be careful of is there's a rock to its right and to its rear. So as the Charlotte robot performs these multi-point turns, it's going to need to be careful not to get stuck on that rock. Appears to be turning just fine though, but it's limited in its space that it has to perform this turn. Again, this is Charlotte on the bottom of the screen and Saginaw Valley State at the top of the screen. The Saginaw Valley State robot drove forward completely out of the starting area and then backed up a little bit. And we can see a little bit of motion from Saginaw Valley. There you see a wheel moving, but not all four wheels are moving. Matter of fact, the front right wheel is moving forward where that rear wheel was moving backwards there. So it doesn't seem like all four of the wheels were in sync just then. You can see the front of the Saginaw robot is lifting. So what it looks like they're doing is pushing their digging mechanism down into the dirt to lift the front of the robot up and maybe help get it unstuck. And North Carolina Charlotte appears to have gotten past the berm, which from this angle you can see it really is a pretty good sized hill. Now they're going to have to be careful about that rock. And look at the suspension system on the Charlotte robot. You can see it kind of wobble back and forth like a teeter-totter a little bit when it when it starts and stops. So they've got a kind of a springy suspension on this robot, it looks like. Now Charlotte appears to be in the digging zone, and look at that spinning excavator. This is a really good angle showing, boy, that's a really powerful and tough excavator. It just pushed down, and now it's raising back up. And you can see the hole that it left beneath. Now maybe the overhead camera will be able to see the transfer of the material onto that belt. And like we saw before, I think it was Michigan yesterday that completely dumped its first load right there on the ground, which initially I thought was a mistake, but then I realized, oh yeah, we don't care about the top stuff. We're only getting scored for the deep, for getting the deep rocks that are buried beneath the top surface, and so that's, I suspect, why the Charlotte team unloaded their haul just then. This overhead camera might give us a little bit of insight into their transfer or dumping mechanism. And I think they're going to run backwards in order to dump onto that conveyor belt and then offload it. That's going to be interesting to see how deep they go before they decide whether they've hit the rocks. Are they going to be able to see whether they've got rocks? Or are they using data from the robot to tell them exactly how far down they've gone? Because the rules tell these teams roughly how far deep the gravel is buried. Meanwhile, the Saginaw Valley robot has lifted its the front of its robot. You can see even from this angle, the front of the Saginaw Valley robot is way up in the air, and you can see its front wheels turning, not both at the same rate. They might be having an issue with their front right wheel because it seems to be kind of starting and stopping. And meanwhile, on the right, Charlotte is going back for, is this their fourth load? I wonder how deep they go before they decide to keep it. I wonder if they're waiting to see a visual indication on their cameras or something like that they've hit the gravel. We're almost 7 minutes into a 15-minute run, So still plenty of time, even though it took Charlotte a little bit of time to get past that berm and to get their robot down into the digging area. Once they got into the digging area, they have been super fast, super powerful, super efficient. You can see dig, dig. It's getting bound up a little bit. It hits a point where they can't quite dig any further. They tried again. Now they're just lifting it up. Oh, I saw some come out that time. I don't know if that was on purpose or not. Meanwhile, in the background, Saginaw Valley appears to be moving different mechanisms on board the robot and trying different things. They're probably troubleshooting back in the control center, looking at the data for all their different motors and actuators to see what's going on with the robot. The Saginaw Valley robot is trying to move. We just saw it kind of move just a little bit just then. Okay, the Charlotte robot is really, really deep now. I'm going to venture to say that they are more than half. They're almost the full diameter of their digging mechanism. You can kind of see the top of their digging mechanism when the front of that robot pops up, and they are super deep. They're almost to the full diameter of their digging mechanism below the surface, which is really, really impressive. Now, are they going to take this load back and trust that there are rocks in it? With a run that is 15 minutes long, we're 9 minutes in and 6 minutes remaining. So we've got a nice overhead view. Look at the slot that they left, this deep hole that they left behind. 5.5 minutes remain. So once they offload this load onto the lander, there is a chance, there is a possibility with 5 minutes remaining that they could go back for more. So let's see how fast this Charlotte robot can unload its gravel. And let's hope most of the gravel actually gets unloaded onto that mesh, that rectangular shaped mesh, which is taking the place of our lander's receiving station. All right, under 5 minutes remain. Meanwhile, the Saginaw Valley State robot, they may have given up on driving all the way over into the digging area. They may be just operating their digging mechanism right here in the obstacle area, just to get some runtime on it and just to get some experience on it. You can see how heavy the Charlotte robot is on its back end. Okay, those look like rocks to me. That looks like some good stuff right there. Okay, we got 4 minutes. We're keeping an eye on the time. We got 4 minutes. Is Charlotte going to have enough time? Here's the thing. Even if they have enough time to get down there, are they going to be perfectly lined up with that hole? What are the odds that they can actually go into that same hole and dig deeper than they just dug? That is not. They're going for it. Look at that. Oh man, that was a really, really fun attempt at driving over the berm. If that would have worked, the crowd here would have just erupted. I bet they did erupt. I'm not in the same room, but I bet they erupted anyway. Oh, lift up their digger and they can get over it. Look at that. Yes, that is so. Look at the judges. They're excited too. All right, that was amazing. So the first attempt was faltered by their center mounted digging drum being too low. But you talk about quick thinking and quick troubleshooting by the team to realize that they could probably get over that berm by just lifting up their center mounted bucket drum was really quick thinking by that team. So kudos to that team. We have just under 3 minutes remaining in this run for these two teams, Saginaw Valley State on the upper part of the screen and University of North Carolina at Charlotte on the lower part of the screen. 2.5 minutes. What is Charlotte going to do with the last 2.5 minutes? So the students that are driving this robot are fully and completely aware of the clock. They have it right in front of them on the computer screen. So they're going to go back and they're going to cross their fingers and hope that they got some rocks and that they still have 2 minutes left. Part of me wishes they had dug a little bit more, but honestly, if I was a student, I would be freaking out and worried that that I was gonna blow it. So it looks like they came back. They still have a minute 45. I don't know. Do you think they'll try another run with their last minute and a half? Or what are they going to do with this last minute and a half? I got a minute 34, 33. What is Charlotte going to do with the time remaining? They don't need to lower that. Don't lower it. Don't lower it. Nice. And look how well they lined up with the hole that they just dug. They went a little past it, but I wonder if the tracks that they made before actually helped them stay in that exact same spot. That's actually possible. Or we could just chalk that up to really good driving. Now, I want to point out the wheels. This is a really good angle of the wheels of this robot. We have 53 seconds. The wheels of this robot do have gripping mechanisms. They have treads, but it looks like the team has covered up their wheels with something soft like a cloth, or it could be a tape. Look at that. 35 seconds remain, and they're going to be able to dump this final load. It looks like we're at 25 seconds now. And let's see if they got lucky and found any rocks. Wow. Looks like there was a couple rocks in that load. 10 seconds left. I don't think there's going to be a time to do anything else. They might run over to the digging area just for fun, or they might just call it right there. And as time runs out, the crowd goes wild in cheering for this North Carolina Charlotte team. What an amazing run. And you can see the judges carefully picking the rocks off of the screen, and they're going to go weigh these rocks. And this Charlotte team is going to get points based on the final weight of these rocks that they were able to bring back to the lander. So congratulations. I want to congratulate both of these teams, not just Charlotte, but Saginaw Valley. They made some progress. They got out of the starting area. Their wheels were moving, at least initially. Their digging mechanism, we saw that working a little bit ago. Their digging mechanism was strong enough; it actually was able to push down and lift the front of their robot up into midair, which probably helped them with some of their troubleshooting. So congratulations to both of these teams. And as soon as we see on our live display what the weight of this haul was from North Carolina Charlotte, we will notify everyone on this live stream. I don't know how long that's going to take to show up on my live screen, but what the teams are going to do and what the judges are going to do for the next hour probably is to take a lunch break. So we're going to continue our live stream throughout the lunch break, try and keep the cameras trained on something at least mildly interesting, and we'll show some more NASA videos during that time. And but don't go anywhere, because this afternoon after lunch, we're going to be running all of our remaining teams that are here in Group 1 competing Monday and Tuesday. We're going to see Iowa State, California State Long Beach, NYU Tandon School of Engineering, Alabama, Miami-Dade, Florida Tech, the University of Akron, the University of Utah, New Mexico Tech, Rochester, Arkansas, and Purdue. So stay with us all day long, and tell your friends about this live stream. We have nearly 140 people watching live right now. Thank you all for watching. Don't go anywhere. Stick around for more of NASA's Lunabotics 2022 Collegiate Robotic Mining Competition.
One of the focuses of the project is to help advance commercial technology. My name is Laura Evans, and I lead a team of researchers in 3D printing the next generation of rocket engines. We can create designs, rapidly look at them, prototype them. We can turn around parts in months. We're looking at two main processes. They both use metal powders to create the part. The challenge is making sure they're just as strong and they're going to work as well as conventional manufacture. We do these hot fire tests, and then we see if it falls apart. We're pushing the envelope so much that things don't work all the time. And it's not like it's a disaster because you learn from it. This is a scanning electron microscope. This is just showing you what the electrons look like as they come off the sample. And I was used to running for a team. So I ran in college, I ran in high school. I met people at NASA who ran. That's also how I got into marathons. I never would have dreamed that I would be working on rocket components. So it's really nice to be able to come to work every day with these researchers who actually developed these materials years ago, and they're still being used in rocket engines and turbine engines, and they're still really valuable in the world.
To go after something as challenging as spaceflight. That's what NASA's all about, is pushing the boundaries, pushing the limits. We really do challenge ourselves to go out and achieve things that nobody else does. My name is Michael Aldridge, and I make history every day. I have the honor and privilege of getting to lead a multidiscipline team that's responsible for the design for thermal protection systems hardware for the SLS core stage launch vehicle. It's the center launch portion of the vehicle so that we can do exploration and we can go deeper and farther and faster. So we're at the Michoud Assembly Facility, which is America's rocket factory. This is where we take raw components and we shape nature into a spaceship. And in this case, the biggest launch vehicle ever devised by humans. And this is pretty intense stuff. For me, personally, the way I learn, I just got to roll up my sleeves and get my elbows dirty. It's kind of a pinch me kind of thing to really see it go from paper to real tangible hardware that we're really going to go fly. Is very exciting for me to really get to be a part of that, to be where I am. I really consider myself fortunate and blessed.
NASA's first Polar Resources ice mining experiment, also known as Prime 1, will robotically look for ice and other resources below the lunar surface. Thanks to data from spacecraft orbiting the Moon, scientists believe that the polar regions contain water ice in the form of ice just below the surface. With the right technologies, that ice is a game-changing resource that can be mined and used to produce propellant and breathable oxygen for future explorers. Under NASA's Commercial Lunar Payload Services Initiative, the agency selected intuitive machines to fly and land Prime 1 on the Moon's south pole. Prime 1 will land near the Shackleton crater to drill into the lunar soil in an area that could contain water ice. Prime 1 is made up of two instruments, Trident, the regolith and ice drill for exploring new terrain, and M-SOLO, the mass spectrometer observing lunar operations. Trident will drill up to 3 feet into the lunar surface, extract lunar soil, and bring it up to the surface. Trident drills to its maximum depth in multiple phases, stopping at different increments. As it reaches each desired depth, it will pause and retract the drill string to deposit lunar soil on the surface for analysis. This is where M-SOLO comes in. M-SOLO is a commercial off-the-shelf mass spectrometer modified for spaceflight. It will evaluate the chemical elements and compounds released from the lunar soil for water and other chemical compounds. Trident will then proceed to the next specified depth and repeat the process until samples at all desired depths have been analyzed for water. If no ice is found where Prime 1 lands, NASA will still collect valuable information about drilling into the lunar soil for a future mission. NASA's Viper, the Volatiles Investigating Polar Exploration rover, will use Prime 1 technology on a mobile robot that will navigate the Moon's south pole searching for additional resources. Prime 1 data will help NASA assess lunar resources to inform future Artemis missions and a robust human presence on the Moon.
Well, welcome back, everybody. We are broadcasting live here from the Kennedy Space Center Visitor Complex in Central Florida. My name is Kurt Lloyd. I'm a NASA engineer, and it's a pleasure for me to be your MC, your host, your narrator, your commentator, whatever you want to call me. And we've just come back from a lunch break, and we have two teams that are getting ready to run their robots for their second attempt. We have Iowa State and we have Cal State University Long Beach teams getting their robots ready in the arena to run on their second attempt. Let's go ahead and take a look at the arena as the students bring their robots into the arena space. On the screen, you can see Iowa State University on the right side and California State Long Beach on the left side of the screen. So both of these teams are placing their robots into our simulated regolith, simulated lunar dirt, simulated moon dust bins. And these robots are getting their second attempt, their second chance at scoring in our Lunabotics robotic mining competition today. We're hopeful that both of these robots are able to leave the starting area and go through our obstacle area all the way to the mining area. Once they're on the far left side of the screen and have crossed, once their digging implement has crossed the line that designates the beginning of the mining area, these robots are allowed to dig down as far as they please in order to get past the dusty crushed volcanic rock and to dig all the way down and find the gravel that we've hidden beneath the surface. Once the robots are able to collect that gravel and drive all the way back to the starting place and deposit those rocks, deposit that gravel onto this grate, which simulates the lander's receiving bin, only then will they get mining points, which count towards placing in this event. So again, the robot at the bottom of the screen is the Iowa State University team, and the robot at the top of the screen is the Cal State University Long Beach team. Here's some fun trivia that I found out about Long Beach, California State University, Long Beach. They have actually had an athlete participate in every Summer Olympic Games since the school's founding, which was in the year 1949. Pretty impressive. You may recall earlier in the competition where we had a robot that had what looked to be, of course, I could be wrong, but what looked to be plastic, maybe even 3D printed buckets on the robot. And while they were digging, it seemed that a lot of the buckets actually broke off or fell off the robot. When I was doing some research and looking over these robots earlier, I couldn't help but notice that this Iowa State University robot at the bottom of the screen, its tracks are all completely made out of steel, and the conveyor belt or track that is around its digging arm, which is at the left side of the robot and actually rotates down below the surface, that track is made completely out of steel. It's a thin steel in order to try and save on weight, but it is steel, and we can see the Iowa State University students measuring the height of those PVC posts that are at the lander. I presume that's because they're going to install sensors on those posts that are a certain height off of the surface of the simulated lunar soil. And those sensors probably are used for some automation on board their robot in order to one reason to put automation on your robot is to relieve the work required by your student operators, relieve some of the pressure required by those student operators. But the more important reason to do automation on your robot for this competition is the points that you will receive if you are successful with your automation. Because automation in this competition is scored very favorably. What's happening right now is both of these student teams have 5 minutes to activate their robots, and they're able to communicate via radios with their fellow teammates that are in the control room just down the hall. Those teammates in the control room do not have direct sight or direct contact with the robot. There we see Iowa State's robot waving hello. Those students in the control room are in a closed room. They only have access to the screens that are in front of them, the screens which they brought to the competition themselves. They're bringing laptops, they're bringing monitors, they're bringing whatever they need to monitor and control their robot. There is one extra monitor in that room that is provided by NASA that gives them an overhead camera view of their robot that they can use if they choose to. And teams that choose to use this lander provided camera will get a little bit of a penalty for choosing to use this lander provided camera. And so there's actually an advantage to teams who choose not to use the lander provided camera if they can handle the job, handle the mission, perform the mission from start to finish without using our NASA provided lander provided camera. They'll get some point advantage in the overall competition scoring technique. I should mention that this is the second run for these teams and the final run in the competition for these teams. Each team in Lunabotics 2022 only get 2 competition runs. Not only that, they get 0 practice runs in our Artemis Arena in the crushed volcanic rock, which is actually different from in prior years. In prior years, we've been able to allow teams to do practice runs and work out some of the bugs and some of the issues. And this year, it's tougher. The rules are a little bit tougher for the teams than they have been in the past, and so this year, teams are not allowed to perform practice runs in this arena. And that's really a little bit analogous to a real mission when NASA designs and creates a lunar rover or a lunar robot or a lunar lander or whatever they're sending to the moon, a payload, an experiment. You can do a lot of practicing here on Earth, a lot of practicing in different facilities, but you only have one shot for the thing to actually work during its actual mission. So that's part of the reason why we're not doing practice runs this year. Just to look ahead before this run starts, after Iowa State and Cal State Long Beach run, we're going to see NYU Tandon School of Engineering and the University of Alabama coming up next. After that run, we'll see Miami-Dade Kendall and Florida Tech. And after that, we will see Akron and the University of Utah. Wow, we are only 15 seconds into this run, and Iowa's robot is all the way across the line into the digging area, not wasting any time. And that, I can't know for sure, but that was very possibly a fully automated trek through the obstacle course. Very impressive for Iowa State. All right, this is exciting because both of these robots appear to be doing very well right up front. So Cal State, Long Beach on the left, and Iowa State on the right. Iowa State's robot really jumped across the line in order to get to the digging area. And now we're hopeful that we will see it start digging. Okay, there's, oh boy, I do not like it when pieces fly off of the robot. That does not look good. Oh, it is. It really looks like it's tearing itself apart. But let's see what we can get. I presume that this robot is still fully automated, and the students are possibly able to see this from their vantage point, or possibly not. This is one of the unique things about this competition is the students, they can't see the robot from the perspective that we're looking at the robot right now. We are not giving them access to this particular camera feed. Oh, it seems like their secondary lifting conveyor may have jammed up, and you can see how a lot of those buckets are turned sideways. They may have the team may have realized their problem, and they may have switched to manual mode possibly. But as I was saying, the students in the control room, they don't have the visibility the great visibility and the great camera angles that we have. If they choose to use the NASA provided camera, it's going to be one overhead camera that is closer to the lander than we're seeing here. So again, Iowa State on the right and California State, Long Beach on the left. California State didn't have any obvious problems getting to the digging area, but we've seen them raise their digging implement, their digging system, which appears to be a series of buckets, maybe chain driven, so a bucket ladder system. But we can see that it's sort of pulling on itself. Maybe when it's being driven, it's maybe getting stuck on something. I'm not sure. It's really hard to tell. On the right, the Iowa State robot is most definitely moving some actuators, and now it's driving. The students may have taken over manual control. They may have, I don't know, that may be still automated. Just based on the way that thing is driving, that thing could be still in automated control. But the thing about robots is most of the time your automated software assumes that everything's working. So it's going to be interesting if they're still in automated mode. What's going to happen when things that are assumed to be working are actually not working? So on the screen, we have Iowa State at the bottom, Cal State Long Beach at the top. So if the Iowa State robot is still in automated mode, the students may be trying to decide how long to let that go. If it's unproductive, how long do you let it go unproductive before you give up and take over manual control in order to try? And they spun a little bit of dust, it looks like. But you know what I think happened is there's a conveyor belt with buckets on it that are in between the front of the robot and the back of the robot. And that's the one that has the buckets turned sideways and at different angles. And I think that one was not working properly. It wasn't at the efficiency that it needed to be. And so not very much of the dirt that they ended up digging, doesn't seem like very much of that dirt actually ended up where it needed to be. which is in the back of the robot. That is a really efficiently driving robot, though. Even in its current state of disrepair, that Iowa State robot has no trouble driving around the obstacles. And sometimes it's hard to tell if a robot is being manually controlled or automatically controlled. But the way this thing drove around those obstacles and basically went over the same path as it did before, I wouldn't be surprised if this if that drive was fully automated. I'm not saying a human couldn't drive like that, but in my experience, human operators typically don't look like a robot when they're when they're driving. Sometimes sometimes it's pretty obvious when an automated routine is being used. Although again, I could be wrong. I was wrong once before, and I'll probably be wrong at least once again in the future. So on the right, Iowa State. On the left, California State, Long Beach. Oh, look at Iowa State going right over the berm. I don't know if an automated routine would have driven right over the berm. They may be in manual mode now. I think they're just playing right now, to be honest. And if I was them, I'd play too. If you know that you can't collect any more of this material, and you know that there's no way you can get any gravel back into the sieve, the grate that's back at the lander, you might as well do some performance testing of your mobility system, right? So they just proved a couple times over that their robot has no trouble driving right over that berm. And it looked like the Long Beach robot might have been actually doing a little bit of digging just then. Neither of these robots is stuck mobility-wise. It doesn't appear. Now the Long Beach robot at the top of the screen, it has what, 12 wheels, and I was unsure how many of these wheels were actually being powered and how many were just passive, but it seems to be a valid design because they didn't have any trouble getting from the starting location over into the excavation location. The Cal State Long Beach robots' troubles appear to be with some sort of a binding, possibly in their bucket ladder conveyor belt type of system. It's not really a conveyor belt. It's it's buckets that are driven around cogs using a chain. But it almost looks like they're binding on something because every time they try and drive, it almost kind of torques the whole robot, or it torques the whole digging system down a little bit. So Cal State Long Beach, with 5 minutes remaining in this run, may be attempting to go back to the lander and go ahead and exercise their offloading system. So let's see how they do there. All right, Cal State Long Beach is on the left. Meanwhile, Iowa's robot, it's not on the screen, but they don't appear to be moving right this second, so we're not really missing anything from them at this moment. By the looks of this overhead view, it looks like Cal State Long Beach kind of hit the jackpot as far as straight line path between the starting point and the digging point. They did hit a little bit of the berm there, and it did not appear to stop them. So good job to them. And as one of the judges comes in to the bottom of the screen, it looks like Iowa State may have called it for this run, as the judge picks pieces up off the robot. Now this is an interesting offloading mechanism that I haven't really been able to fully figure out in my head yet. There's conveyor belts on the right and on the left of their bucket drum system that lower and raise. But what I'm confused about is how does the soil and how does the gravel end up on those conveyor belts? I'm going to presume that since the judge is sticking his hands in the Iowa State robot, that they've been e-stopped. Because I know I wouldn't stick my hand anywhere near that robot if it was still active. That thing is a beast. So we noticed when the Iowa State robot first started its central, I'm going to call it a lifting conveyor, a bucket ladder system that's in the middle of the robot that doesn't actually do the digging, but does the lifting from the digger in the front of the robot to the hopper in the back of the robot. There were all kinds of what looked like metal pieces, bolts, maybe parts of their bucket. There were lots of pieces that seemed like they were flying up in the air. So I suspect that the judge is trying to find all the pieces and make sure that we don't have any rogue leftover robot pieces in our arena that could get in the way of the next competitors. Meanwhile, at the top of the screen, Cal State University Long Beach robot is, they did line up to the depositing area, the dumping area, and they lifted their two conveyor belts that are apparently able to offload the material. I did not see any material be deposited onto the lander, but that's actually not surprising because I do not recall any material being lifted by their bucket ladder system. I think Iowa State may have given up and they're just bringing the robot back maybe towards the entrance so that they can easily get that robot out of the arena. We're under 30 seconds left in this run. So I think we've probably seen all we're going to see out of these robots. But kudos to both of these teams, because just getting your robot out of the starting gate, getting your robot through the obstacle zone, getting your robot into the digging area, both of these teams were able to do that before Cal State Long Beach had some issues. And Iowa State, amazing. They've shown an amazing ability to dig quickly, to dig deeply. They just had a problem with the middle inside leg of their mechanism. Their digger appeared to work fine. Their dumping elevator seemed to work fine, but they had an elevator bucket ladder system in between those two systems that appeared to have some some serious issues, and it appeared to fall apart right before our eyes during the run. But regardless of those issues, kudos to both of these teams. Congrats to both for getting this far and for having the success that we just witnessed. The teams we're going to see next are New York University Tandon School of Engineering, NYU Tandon, and we're also going to see the University of Alabama. So don't go anywhere. Those two teams are coming up next. And tell your friends, share the link to the live stream. We've got over 170 people watching right now. Thank you all for your interest. We appreciate you sticking around with us. We appreciate your excitement and cheering on your teams in the chat. And so don't go anywhere. We will be right back in just a few minutes with the next two teams. You're watching NASA's Lunabotics competition. We're live streaming from the Kennedy Space Center and Visitor Complex. And what you're seeing on the screen right now are about half of our teams that are here today, because we don't have a camera wide enough to show you the whole room. But we have, this week, we have nearly 40 teams competing in this NASA Lunabotics competition. We've split them into two groups. Half of them are competing. They competed yesterday and are continuing to compete today. And then we will take a break from live streaming tomorrow while we swap out these Group 1 teams with a new set of Group 2 teams. And those Group 2 teams are going to compete on Thursday and Friday. And we will be live streaming again on Thursday and Friday after taking a break from our live stream tomorrow. We're waiting for our next two teams to enter the arena, and we're watching the teams who are in their robo pits, getting their robots ready for their next run, or in a few cases, the teams are finished with both of their runs and are just resting and relaxing and recovering from such a crazy and busy last few days. The two teams that will be competing next are NYU Tandon and Alabama. After those two teams, we will see Miami-Dade Kendall campus and Florida Tech. After that, we will see the University of Akron and the University of Utah. And looking even beyond that, looks like we will see New Mexico Tech and the University of Rochester. Now, as we wait for the teams to enter the arena, I can fill a couple minutes by telling some of the robotic jokes that I have compiled. So hopefully the students that are in the RoboPits will be able to react either favorably or unfavorably as is appropriate based on these jokes. So here's my first robot joke, and hopefully they can all hear me. So what do you call a robot that always takes the longest routes? What do you call a robot that always takes the longest routes? It's R2D2. I'm looking for a reaction. Nothing. Either they hated that joke or they can't hear me at all. All right, let's try another one. Here's another robot joke. The red wire said to the black wire, "Why are you so sad?" The black wire replied, "I've been grounded." Yeah, they like that one. Okay, here's another one. Why was the robot angry? Why was the robot angry? Because somebody kept pushing its buttons. All right. We're saved by the bell because it looks like we have our first team entering the arena, which means I don't have time to tell any more really lame robot jokes. This is going to be on the A side. This is going to be NYU Tandon School of Engineering. NYU Tandon is located in Brooklyn, New York. This school was formerly called NYU Poly. And two notable alumni from NYU Tandon are Charles Camardra, a space shuttle astronaut, and Thomas J. Kelly, who you may know that name because Thomas J. Kelly designed and built the Apollo lunar module. Now on the left side of the screen, or the far side, you see the University of Alabama bringing the robot into the B side of our arena. Now, yesterday when these robots had their first run, neither was actually able to bring any of the gravel back into scoring position. But we have high hopes that any issues that occurred yesterday have been able to be troubleshot and fixed by these teams. And we're hopeful that both of these teams are going to have success in their second runs. So those listening, those watching are probably on the edge of their seats wondering how much gravel the University of North Carolina at Charlotte was able to bring back and deposit. So my screen, which is not the official judge's determination, this is just data that's being passed around internally. My screen says that, well, first of all, let me back up. Yesterday, Michigan Tech ended up, I was earlier saying 0.3, but I asked our technician if he could increase the resolution of that number. And so now my screen says 0.31 kilograms was what Michigan Tech brought back yesterday. And the University of North Carolina at Charlotte is showing just a hair under that at 0.295. So both of those teams getting very close to a third of a kilogram with their runs. I just want to thank the people in the chat who took pity on me and laughed in the chat at my really lame robot dad jokes earlier. Appreciate y'all. We are about halfway through the 5-minute setup time given to each team. During this 5-minute setup time, teams are allowed to set up their equipment, their router, activate their robot, and they're able to communicate with their teammates in the control room using the radios that we provide. And they're able to verify that everything is working properly on the robot before their run starts. On the left side of the screen, it looks like the Alabama team are installing a visual indicator, a visual marker that their robot will use to figure out where it is in 3D space in our arena. Robots that use automation, in addition to wanting to know where they are in 3D space, most of them need to scan the area in front of them in 3 dimensions in order to decide whether there are obstacles like rocks and craters in front of them in order to avoid those obstacles. Now it looks like the students are leaving the arena after they've checked out the robots and verified that everything appears to be working properly. And now, from this point on, when you see those robots move, they're either being operated autonomously, meaning nobody's driving the robot, it's figuring out all on its own where it is and where it needs to be and getting itself there. Or the students who are in our control room down the hall and don't have direct visible sight into these robots are controlling them using remote telemetry. For example, data that's coming from motors and sensors and live video feeds that might be coming from onboard cameras. Or the teams could decide to use a live video feed provided by NASA, which emulates a camera positioned near or on the lander. Now, as soon as our judging team verifies that everything is ready to go with all of our equipment and all of our judging staff, we will start this run between University of Alabama on the left and New York University Tandon School of Engineering on the right. we can see both of these robots are moving out of the starting area. Alabama at the top of the screen and NYU Tandon at the bottom of the screen. Now that NYU Tandon robot, I don't know that it has enough ground clearance to drive over that berm, so it's going to have to go to the left towards the bottom of the screen in order to avoid that berm. Meanwhile, the Alabama robot has appeared to have recognized all the obstacles and successfully avoided them all. Now this Alabama robot appears to be choosing its excavation location very carefully. It's going right to the far edge of the arena. And we're waiting expectantly to see this Alabama robot deploy its excavation system. It's a very impressive excavation system, and start lowering it into the ground. And look at that. That's pretty impressive. It's a very high-speed belt or conveyor that has what I believe are metal buckets attached to it. And look at that thing dig down. Look how deep that thing is digging. It's fast too. It's almost like it barely feels any resistance at all. It's cutting through that tough regolith simulant like butter. Now it has lowered its digging mechanism very low, and it appears to be driving backwards. It's hard to tell. Now it's going to be even harder to tell as duft becomes lofted into the air. Okay, I think it drove backwards. I may be wrong, but I think it might have driven backwards a little bit, and now it's raising its digging mechanism. All right, now on the lower side of this part of the screen, we see NYU Tandon has lifted up their auger-shaped, their spiral-shaped auger digging mechanism. I don't know if they're going to try and dig there just for fun. Look at the Alabama robot at the top of the screen. The whole chassis just lifted up. So while they were digging, their whole chassis like lowered down. I don't know if that's for stability or for some other mechanical or technical reason. Let's see if this Alabama robot can quickly and easily make it back to the starting zone. Meanwhile, the NYU Tandon robot, they looks like they've deployed their auger digging mechanism, but if you look at the tracks on the ground, they have been unable to successfully turn left. They may be having some control issues because they've been driving back and forth on the same arc so far for this entire run. Now we're 4 minutes in to a 15-minute run. So do the math. If Alabama in the first 5 minutes is able to dump or deliver this first load within the first 5 minutes of the run, that means they'll be able to do 2 more cycles of that in a 15-minute run. So now the robot's job at this point is to align itself as closely as possible and as nearly linearly as possible as it can with the receiving bin. It's paused. It may be scanning the environment. Okay, it's lifting up its chassis again. Now, Now we should be able to get a pretty nice view of its offloading mechanism, which I believe is I'm trying to remember, I believe it's a belt to the left of the red track with the buckets that you see on the screen, but I may be misremembering the details of this robot. You can see above the wheels and below the track, you can see like a clear plexiglass side, and I believe we're seeing the gray material inside there, which I believe is the simulated regolith, the crushed volcanic rock that this robot has been able to collect. Now, how did they get that regolith unloaded? Okay, we're starting to see a belt mechanism. Oh, yeah, I remember now. So this is an incredibly designed system. Now that you can see through the clear plexiglass, you can see that there are shelves. It's a conveyor belt, but this conveyor belt is very unique. It actually is like a mesh, almost like a chainmail, but it's not made out of metal. It's made out of nylon or plastic. Look at that haul. Look at all those rocks that are sitting there on the lander. That is amazing. Looking at our time, we're 6:45, almost 7 minutes into a 15-minute run. So Alabama robot has 8 minutes left. You see the judges very carefully making sure that these rocks get counted for this team. They're going to go ahead and offload them possibly, and make sure that all those rocks get weighed for this Alabama team. So we're right in the middle, 7.5 minutes in, 7.5 minutes remaining for this team. So not only did this Alabama robot do a really amazing job of excavating, I suspect that this is all still completely automated. I'm fairly positive that this is all automated based on the way I'm seeing this robot react. And that means not only will they have a really good score just based on weight, but then they'll get the amazing bonus points for being fully automated. Now watch how deep this robot goes. I will say that for a robot to be able to go this deep, it has to have some fairly significant reactive forces. So it may be a fairly heavy robot. Watch the robot drive backwards slowly. This is an amazingly well thought out concept of operations. It digs down and then it drives backwards as it's digging. And look at how hard this robot is working. This is a very powerful robot. I will say though that if another robot came out later and got the exact same amount in kilograms that this robot did, and if the other robot turned out to be lighter in its overall mass, we do score these teams on the lightweight, how lightweight they make their robots. We also score these teams on how much power they use. So if a robot is lighter weight than another robot, all else being equal, the lighter weight robot has an advantage. And if a robot uses less power in its run, all else being equal, the robot that uses less power would get an advantage points-wise. But that assumes that another robot would be able to haul and deposit this much gravel that we just saw from this Alabama robot. We're 10 minutes in, 5 minutes remaining. So, boy, if depending on how fast this robot is, would it have time to do a third run? Even if it didn't, this is an amazing Amazing 2 cycles. Watch out for that rock. Yep, it saw it. It saw the rock. Now, how fast can it line up with the depositor? And how fast can it decide that it's in the right place and go ahead and offload? Here's where it paused earlier. So we're 10.5 minutes in, 4.5 minutes remaining. Guess it decided that it's in the right spot. And here goes the offload. Now look at the clear plexiglass in the middle of the robot. You can see, you'll be able to see the gray regolith disappear and the belt with the shelves or flaps once all the simulated regolith is gone. All right, less than 4 minutes remaining. What is this robot going to do? I don't know that the robot is keeping track of the time, although it's possible. Does the robot know that it just took over 5 minutes for each of its first 2 runs and has only 3.5 minutes left for this last run? Is it going to act any different on the last run than it did on the first 2 runs? Notice how perfectly spaced this robot knows exactly where it's going. I bet it goes to the left of those 2 holes if I was a betting man. In order to, and I bet it's just perfectly spaced away from where those other ones. This robot knows exactly where it is in 3D space, and it knows exactly where it's going in 3D space. Two minutes and 40 seconds remain. So, as amazing as this robot is it going to run out of time, or is it smart enough to maybe dig for a shorter amount of time than it did earlier because it knows that it is short on time? 2 minutes and 20 seconds remain in this run for Alabama and for NYU Tandon. And if this robot has been working autonomously for this entire run, it pays off for the students to stay hands-off and let it, quote unquote, fail. Let it not get back with this last load, because the points they'll get for having a completely fully autonomous run for all 15 minutes, those points outweigh the points they would get by dumping this last load, I believe. So we're down to 1.5 minutes. I don't know, this robot may be almost finished digging with 1:20. It could almost get back. I don't know if it'll have time to get back and dump, but I think it has time to at least get back to the lander. We're down to 1 minute remaining in this run, and NYU Tandon's robot is still moving, but sadly it hasn't been able to get down to the digging area. This is an amazing run for the Alabama team. Okay, the robot's about to drive back. It only has 30 seconds left, though, which tells me that they just are probably not going to have enough time. But boy, if they had maybe 30 more seconds, they might have been able to get this third load all the way back to the lander and deposited. We're down to 5, 4, 3, 2, 1. That's it. That's a 15-minute time for these two teams. Wow. That's all I can say about this Alabama robot and this Alabama team. This is just a really high performing robot. Um, it's powerful. It didn't have any trouble um, moving on this very unique material. It didn't have any trouble digging in this very tough material. Didn't have any trouble recognizing obstacles and avoiding them. Didn't have any trouble missing the lander, lining with the lander, and knowing exactly where it needed to be in order to dump its load onto the lander. So amazing run for University of Alabama. And NYU Tandon, there's no need for them to be um, sad or embarrassed. Their robot, um, they have they have created a robot that drives around in simulated lunar regolith. We saw several of their mechanisms actually move, and that is that is a real um, kudos to NYU Tandon just for getting this far, for getting a robot that they were able to drive around in the bin, even with the issues that they had and the limitations that we saw. Um, Kudos to both of these teams. So looking ahead on our schedule, the two teams that should be coming up next are Miami-Dade College at Kendall and Florida Tech. Both of these teams will be coming up in the next few minutes. So don't go anywhere. Stick around. You're watching NASA Lunabotics 2022 live streaming from the Kennedy Space Center Visitor Complex here in Florida. I bet they laugh at my jokes now. Let's try another one. What do you call a pirate robot? What do you call a pirate robot? R2D2. This isn't a robot joke. This is a space joke. When I was little, I actually wanted to become an astronaut, but my parents told me the sky was the limit. Aww. All right, only a small percentage of the students in this competition are going to laugh at this joke. How many programmers does it take to screw in a light bulb? None. That's a hardware problem. Wah, wah. So, did you hear about the restaurant on the moon? Good food, no atmosphere. Well, at least the people on chat are appreciating my jokes. We have about 175 people watching us online right now. Thank you all for watching. We are so excited that you found this live stream and that you're watching it and that you're telling your friends and family about it. Our next two teams, if you want to think ahead, are Miami-Dade College at Kendall and Florida Institute of Technology. And then after that, we have the University of Utah getting ready to bring in their robot. I do not have anything on my screen beyond that, but it's possible we might see later Akron, we might see New Mexico Tech, we might see Rochester, we might see Arkansas, and we might see Purdue show up on the schedule. So stand by, don't go anywhere. You are watching NASA's Lunabotics 2022 competition. What you're seeing on the screen now are our next two teams, Florida Tech on the left and Miami-Dade Kendall on the right. These two teams are getting their robots ready to run their second run, their final run of the week. Each team's competing this week get 2 official runs in our Artemis Arena simulated regolith bins. And regolith, if you don't already know, is a fancy scientific word that we use to describe lunar soil. And so we're simulating lunar soil in these bins using many, many, many tons of crushed volcanic rock. But under the crushed volcanic rock, we have put gravel, rocks about the size of an inch or two. And it's the gravel underneath the crushed volcanic rock that these robots this week are here to dig, excavate, bring to the top, collect, and then carry back to the lander and deposit onto the lander. That's the job of all the robots this week. And they will get scored based on what is the weight of the gravel that they bring back. We're looking live at the RoboPits where teams are either preparing the robots for the next run or they're just relaxing and enjoying the show because they're all finished with their 2 runs. Now, is anybody in the RoboPits interested in finding out how much gravel the University of Alabama just deposited onto the lander? Anybody want to know how much they brought back? Anyone? Can they hear me at all? Who wants to know how much Alabama brought back to the lander? I don't think they can hear me because I think they want to know. All right, put up the graphic. Alabama brought back 5.2 kilograms back to the lander. Really, really impressive. The caveat here is I am not an official judge. This may not be the official number, and I am not in charge of giving any team their official score. But this is the number that is showing up on my computer screen right now. Now back to the next run. Miami-Dade, Kendall on the right, and Florida Tech on the left. These student teams are about halfway through their setup time, where they're given an opportunity to power on their robots, activate everything that needs to be activated, and communicate back to the students in the control room to verify that everything appears to be working properly before we start their run. Each run is a timed 15-minute run. During those 15 minutes, these robots they're needing to go to the complete opposite end of the arena that they start in, and they need to avoid obstacles like rocks and craters on the way in order to get into the digging area. Once they're in the digging area, they need to dig down as far as they can in order to reach the buried gravel that we've buried beneath the surface. And that gravel is simulating icy regolith, or chunks of ice buried beneath the surface. If those robots can collect this deeply buried ice and bring it all the way back to the lander and deposit those chunks of ice onto the lander's hopper, their wire mesh grate, they will be scored based on how much mass, how many kilograms of ice they're able to bring back. So as we see the students exit the arenas, we should get this run started in just a few minutes. And just for those that want to look ahead, after this run featuring Florida Tech and Miami-Dade Kendall, we will have a run that involves Utah running by themselves. And then we will have a run with New Mexico Tech and the University of Rochester. And then we will have a run with Arkansas and Purdue. And looking ahead, that should be our entire field. So we basically have about 2 hours from now, we should be finished for the day, which is really good. That means we'll be done around 5 p.m. Eastern, which puts us right on time with our originally scheduled plan. While we're waiting for this run to start, I want to give another shout out to the 4 afternoon arena judges. We've got Tom, we've got Austin, we've got Joe, and we've got Nathan, our full-time afternoon arena judges, doing a great job. They're off. These robots have 15 minutes to perform their task, and the Florida Tech robot at the top of the screen seems to have dug in a little bit. Let's see if they can get themselves out of that predicament. And we have yet to see the Miami-Dade Kendall robot at the bottom of the screen move yet since this run started 45 seconds ago. It looks a little bit like the Florida Tech robot has dug itself in a little deeply. It may have bottomed itself out. It may be high-centered. But there's so much time left in this run. Let's see if they can maybe do something to fix that situation. You may have noticed how easily it was for that robot to start spinning its wheel and digging itself down into this simulated lunar regolith. Lunar regolith is very light and fluffy on top, and it's actually not too difficult to jostle it, fluff it up a little bit, and get it to kind of fluidize and get yourself kind of sunk down into it. We're seeing some movement now from the Miami-Dade Kendall robot at the bottom of the screen. Look at Florida Tech popped right out of that hole that they were in for just a minute. We're 2 minutes into a 15-minute run. We've seen the Kendall, the Miami-Dade Kendall robot move a little bit. Some of its actuators moved. That's a hole right there, Florida Tech. There you go. You don't want to get stuck in that same hole again. Now, from this angle, it's hard to tell whether all four of their wheels are moving. Okay, I can definitely see 3 of their 4 wheels moving. It's possible that all 4 of them are moving, but they don't all seem to be moving at the same speed with the same power. But maybe they can rock themselves back and forth and get out of this spot. And now we can see the Miami-Dade Kendall robot. Its digger has moved up and down a couple times. Its dump bed in the back of the robot has moved up and down at least once. So the students are obviously able to send commands to this robot, and the robot is able to respond to those commands. Just wondering why the wheels are not moving at this point. And the students may be troubleshooting that as we speak. So Florida Tech at the top of your screen, Miami-Dade at the bottom of your screen. Both robots are moving. Florida Tech has moved a couple robot lengths ahead, but has dug itself in, I think, twice now. Let's see if it got itself out before. Let's see if it can get itself out again. Five and a half minutes into this 15-minute run for these two teams. Their last run of this year's competition. Their second and final run for this year. Hopefully they can fix whatever issues they're having and get down to the digging area and dig down to that gravel that's hiding beneath the surface. We can see the Florida team is now lifting their dump bed. Both teams actually have lifted their dump beds. So one possible reason for doing that is just because you've given up and you're just testing your robot to the max, to the best of your abilities. But it's possible they haven't given up. And one thing that can happen when you move your different systems around and you articulate all the different things that can be articulated, sometimes it can be just enough to change the center of gravity of your robot and possibly, best case scenario, make a wheel, make the robot shift and make a wheel touch that wasn't touching before, and possibly get yourself unstuck. Again, the robot at the top of the screen is the Florida Tech robot, and the robot at the bottom of the screen is from Miami-Dade College, Kendall. A couple notable alumni from Miami-Dade College, Kendall. Bob Vila, who's a home improvement TV show host that was very popular in my youth. He got his degree from Miami-Dade, Kendall. Sylvester Stallone, the very popular actor, also my generation. Probably a lot of the students in the room probably don't know, maybe not know who that is, but he sure was popular when I was in high school and college. But I know everybody in the room is going to know the actor Oscar Isaac, who played Poe Dameron in Star Wars. So go Star Wars, beat Star Trek. We're about 10 minutes in, 5 minutes remaining in this run. So still time to make something happen if something is able to happen with these robots. Florida Tech's robot did move out of the starting position, initially got its front back wheel is currently, it got past that by moving its digging mechanism around a little bit, was able to get past that, and then kind of got buried again. The front left wheel is completely free spinning, completely in midair, not touching anything right now. If the back wheel was actually doing positive work and actually moving the robot, it might be able to get out of there. But I wonder if they've had some sort of an issue or a failure with their drive mechanism somewhere. Some of the possible failure modes in these robots would be, a blown fuse is one failure mode. A more of a mechanical type failure might be the wheel actually slipping where it attaches to the axle, where the axles may be moving just fine, but the wheel is just not being turned with the force that it is intended to be turned with. Other possible problems are software bugs that crop up only in certain circumstances that maybe just weren't found during testing earlier. There's a lot of links in this chain that all have to work correctly in order for these robots to succeed. want to thank all of our folks that are watching our live stream today. We have nearly 200 people watching right now. And I should apologize to all the Star Trek fans. Didn't mean to throw shade in your direction. Star Trek is a great show. It's just that Star Wars is better. You're hearing the opinions of Kurt Lloyd, a human individual, and not the opinion of NASA, the federal agency. Two minutes remain in this run. So sadly, it does not appear that either of these teams are going to be able to, in the last couple minutes, recover from the issues that they've had and get all the way down to the digging area and bring some rocks all the way back to the lander. But I want to congratulate these teams for getting this far. I mean, creating these robots and getting here, proving using a proof of life video that your robot actually works and does what it was designed to do, getting past all of the required documentation, the project management plan, the systems engineering paper, the public outreach that teams are required to do, and creating a report on that public outreach. Submitting a proof of life video to prove that your robot does actually work and all the mechanisms work as designed. And we can see both of these robots are moving right here in front of our eyes. It's just that they weren't quite able to perform the mission, this complex, very difficult mission that we've asked them to perform. I still want to give kudos and congratulations to both of these teams for making it into this Lunabotics 2022 competition as the time winds down on their second and final attempt. Looking ahead, our next two teams that we're going to see in our arena are New Mexico Tech and the University of Utah. So don't go anywhere. Stay with us. Stay online because you're watching NASA's Lunabotics 2022 competition streaming live from NASA's Kennedy Space Center Visitor Complex here in sunny, happy, lovely Central Florida. You're seeing a live shot from our robo pits where teams have been working feverishly for the last 2 days, actually 3 days, because they got here on Sunday, preparing their robots for the competition this week. And as we get down to just the last several runs of our teams, some of our teams are packing up and heading back home. But don't go anywhere yet because we still have more teams coming up. The next 2 teams that should arrive into our arena soon are New Mexico Tech and the University of Utah. Then after that, we will have the University of Rochester, running alone. And then our final run of the day is going to be Arkansas and Purdue. So don't go anywhere. We will return to our live commentary broadcast as soon as our next 2 robots are getting ready and show up at the arena. You're watching NASA Lunabotics live feed 2022. On the screen, you're seeing New Mexico Tech. They've put their robot into the arena, and soon we should see the University of Utah students show up with their robot and put it in on the B side of the arena. And looking ahead, after this run with Utah and New Mexico Tech, we're going to see the University of Rochester running just by themselves without another team running in the other side of the arena. And then our very last run is the one after that for the day, and that's going to be Arkansas and Purdue. So some folks may question what happened to Akron. Sadly, they've decided to bow out. I don't have the details, but they're not going to be competing in the competition today, sadly. So New Mexico Tech and Utah are in the arena right now, getting ready. Then we'll see Rochester just by themselves, and then we'll see Arkansas and Purdue to finish off our day today. We just saw the University of Utah students, U of U, lots of U's there. Put the robot into the bin. That's the robot on the left. It has a really unique mobility system, a kind of a rocker bogie type system similar to the Mars rovers, but it's spaced out and staggered. The center wheel is farther outside the robot's center line than the front wheel, although those two, actually I take that back, both the front wheel and the center wheel are on the same center line, but it looks like the back wheel is inset. This is a really interesting mobility design and suspension design for this robot. And this robot yesterday had some issues where it kind of got itself dug in at the starting block. So I'm hopeful that we'll get to see this robot drive across the field with the obstacles and get down to the digging area and show us what kind of a digger it has. Which looks like a rotating bucket drum system at the front of the robot, but I'm assuming that the bucket drum system is able to angle downwards and go below the surface, but it's going to be interesting to see how that robot sets itself up for digging. At the bottom of the screen is the New Mexico Tech robot, and you can see it has a really long auger tube centered on the robot, and its mobility system is a rubber track. The students test out their robots. You can see the auger. You can actually see through the translucent auger tube, and you can see the auger rotating there as the students are checking out the robot and verifying that everything's ready to go. The students are about halfway through their 5-minute setup time for their robots. As soon as both teams are satisfied that their robots are ready to go and everything checks out, they will exit the arena and give the judges a chance to do some final checklist items, and then they will start the 15-minute run for these two teams. Again, New Mexico Tech on the bottom of the screen and the University of Utah at the top of the screen. And we have motion. Both robots have moved. And New Mexico Tech robot already crossing over its starting line. The Utah robot at the top of the screen, we did see it lift its head up a little bit. This is the mechanism that it uses to raise and lower that center-mounted rotating bucket drum digger is pretty interesting. I'd like to get a closer look at that robot later on in the pits to see if the whole center of the robot is rotating around the rocker bogie suspension, or if just part of the robot is rotating up and down. Now, I should mention that at the bottom right of the screen, you see those black and white barcodes. That's usually an indication that the robot is using those barcodes to figure out where it is in the arena, which is often an indication that the robot is using at least partial, if not full, autonomy. That being said, it is possible for a team to use barcodes like that to give them real-time feedback as to where the robot is in 3D space, even if they're completely manually stick driving the robot. So there's no guarantee that it's autonomous just because those barcodes are there. But by the fact that the robot is being very, very careful, very slow, sort of implies to me that this is an automated routine, because in my experience, automated software is a lot slower and careful, meticulous, repetitive. Oftentimes, automated software sticks out like a sore thumb compared to an actual human. Oh, look at Utah's robot deploying its wheels. So I was just saying to my coworkers here in our broadcast room that this Utah robot's wheels are so close to its center line that it's almost unstable. Its wheels are so close. So what it's done is it has started with its wheels rotated inward towards its center line, but it has a mode where it deploys those wheels outward, which adds stability to the robot. New Mexico Tech at the bottom of the screen, very slowly, very carefully avoiding the berm, which is on its right, which is a long-ish hill that the judges have created. The Utah robot appears to be digging itself in a little bit. I hope it can get itself out of there, though. So Utah on the top of the screen and New Mexico Tech on the bottom of the screen. That New Mexico Tech robot, if it's fully autonomous, is probably staring at that rock in front of it. Also knows about the berm to its right, because obviously it didn't just drive straight over the berm. So now I'm assuming that the autonomy software is trying to figure out exactly where it can drive in order to avoid both that rock and that berm. So it's probably doing some calculations right about now. Meanwhile, the Utah robot at the top of the screen is decided to lower their digging arm into the ground, possibly not necessarily to dig right there, but possibly in an attempt to help get those front wheels unstuck. Let's see if they're able to make any progress. New Mexico Tech robot at the bottom of the screen has basically come all the way up to this rock and is starting to turn to the right. And it looks like it has successfully avoided the berm on its right and the rock on its left. So slowly but surely, slow and steady sometimes wins the race. Am I right? Plenty of time. We're only 3 minutes into this 15-minute run, And so New Mexico Tech has 12 full minutes now to bring that auger into its digging position and into, as long as it's inside the digging area, it's allowed to do that. And dig down as deep as it can and pull up as much gravel as it can, and then translate all the way back into the starting position and offload its haul onto the lander. This New Mexico Tech robot making really good progress, completely avoiding all the obstacles. We've put rocks into our obstacle zone, we've put craters into our obstacle zone, and we have also put a berm, which is a hill, a linear hill, into our obstacle zone in the middle of both of these arenas. You can see New Mexico Tech's auger tube raising up. It's probably going to go vertical or near vertical. You can see it spinning, the auger spinning. I love that they used a translucent or clear tube so that we can actually see the inner workings of their digging system. You see the front of the robot lifting up just a little bit as it pushes down. The weight of that robot is actually going to help it push that tube down into the crushed volcanic rock, which is a simulation of lunar soil. And you can see this this powder, this gray powder, being lifted up inside that clear tube by the auger. This is a pretty efficient way to dig in this granular soil. We're 5.5 minutes into our 15-minute run for New Mexico Tech on the screen, prominently on the screen, and University of Utah in the background. Haven't seen the Utah robot make much progress since they sort of partially buried themselves in the starting gate. We did see their wheels deploy by spinning around from inside the robot to outside the robot. And that was really impressive. But then their robot appeared to, you can see how deeply the front left wheel is buried. It is almost completely buried all the way up to the top of that front wheel. And that is not easy to do because that means your axle, whatever that wheel is attached to, has to be buried also. And that robot has really, really buried its front wheels in a bad way, I'm sad to say. And I don't know if they'll be able to get out of that. Okay, look at their plunging mechanism. New Mexico Tech's auger is on a set of rails, and it lowers down and it plunges down, and it appears to me that it is probably all the way down as far as it can go. And you can see it bringing up this gray soil, this gray. Well, you can see some flexing in their clear see-through tube. Wow, look at that thing flex. There are some serious forces going on there. I'm not a mechanical engineer. I'm just a software guy, but boy, look at that clear tube flex back and forth as this dirt, this crushed volcanic rock, and possibly gravel, 1 or 2 inch sized gravel, is being pulled up in that tube. At first, I was thinking that this tube was like solid plexiglass, but now I'm not so sure. It must be something much more flexible than a plexiglass tube. It almost looks like a very soft plastic in this in this view. I hope it can hold up. It is really, really flexing a lot. So I'm not sure. Are we able to see anything in the overhead camera view of any material being actually transferred out of this auger onto a plate or a platform? It seems like there's a pile. It seems like there's a pile there that might be the soil. It's really hard to tell from the resolution and the distance of this camera. Yep, there was a rock that just fell. So this is interesting. Is this robot somehow able to bring up a mixture of soil and rocks and somehow separate the two and only let the rocks through, only let the gravel through onto their dump bed? Or is it dumping both a mixture of the soil and the rocks? Kind of hard to tell because we don't have a camera that we can use to zoom in super close and see that detail. But we can, this is impressive. We can see some significant sized rocks, even with our low resolution camera from this distance. We can see these lighter colored rocks, almost white colored rocks, being dropped in this robot's dump bed, which kind of tells me that they might have some sort of a system of separating the soil, the smaller particles, and the bigger particles. We'll have to talk to this team afterwards if we can, and see if we can learn more about their design. So, did they start to raise it? I'm trying to decide what. I think they've started to raise. Yep, they've started to raise. They may be done with this cycle. We're 10 minutes in to a 15-minute run, so they probably need to cut bait and run. So it's possible that this is still fully autonomous. So what I suspect they're going to do is pull that auger all the way out of the ground. Something seems to be binding, though. Uh-oh. You can see it. When it tries, it kind of torques to the right a little bit. That is never a good sign in mechanical systems. Oh, okay. It made some progress there. So keep doing that, what you just did. Keep doing that. But you got to do it fast because you've got 3 minutes and 45 seconds left to drive all the way back to the starting point and unload those rocks onto the lander. This is New Mexico Tech. Rookie team. As far as I know, this is the first year this team has ever competed in NASA's Lunabotics competition. And boy, this is an impressive robot. It seems that they are slowly but surely pulling their auger out of the system. Oh no, don't. Okay. It would be okay to change the angle if it's the angle that's causing it to bind. Oh, look at that. Look at that. They just got the thing unbound, either by changing the angle of it or by changing the robot's position, or a little of both. I'm gonna go out on a limb and say that the students have given up on autonomy and are now stick driving the robot. But I could be wrong. All right, time is running out. We got 2 minutes and 15 seconds to get this robot all the way back to the starting position and offload these rocks that we have collected. So time is of the essence. They're not even going to wait until the auger is fully retracted. they're going to start driving, which is what I would do if I was stick driving this robot. So that's another indication that this is more likely being stick driven, but they're kind of getting in their own way by leaving a little too soon. They gotta pull that auger back a little bit more if they want to. Here's the thing, and I've said this before: the students can't see this angle. We have the best view of anybody in the world because nobody in the room can see this angle. The students that are controlling this robot, assuming that they are manually stick driving this robot, they can't see this camera angle. They're basically seeing the overhead view from way over there by the lander, and so they may not have a really good angle to see how much that auger is dragging and holding them back. The other possibility is that I'm wrong and they still are in fully autonomous mode because they want to try and get the maximum points out of this run. And it's possible that the students are still hands off, cheering on their robot as loudly as they can, hoping that it will hear them. We're down to 40 seconds remaining. It's starting to look unlikely that they're going to make it all the way back to the starting position. Oh, that's a pretty powerful system there that's essentially at that angle able to lift the front of the robot up in the air. So time is starting to run out on this team, New Mexico Tech. In the back of in the background, we have University of Utah, who kind of sort of started coming out of the gate strong up until the point where one of their wheels started to dig in, and a scary situation ended up getting worse, and they ended up basically completely burying the front of their robot and were basically not able to get out of the starting zone. But I want to compliment both of these teams because Utah's robot is really impressive. The way that those wheels started out tucked in, and that's probably because they probably started out tucked in because the starting volume limitations and size limitations of these robots are fairly limited. So they probably wanted to create a larger robot than they were allowed to. And so what their solution may have been was to create a robot that starts out the size that is allowed in the starting zone and have it expand to the size of the robot that they really wanted to compete with. And this is completely allowed in the rules as long as your robot starts out within the volume that it was required to start out as. It's completely legal, completely within the rules to have your robot deploy, expand, change shape into whatever it needs to do in order to complete its mission. So great job, University of Utah. Sad that you didn't actually get down to the digging zone, but real proud of you for what you've accomplished here in this competition. And New Mexico Tech, wow. This robot, I'm really impressed with this robot. You should be very proud, even though you were not able to bring those rocks back. We should be able to see handfuls of rocks come out of this robot. And just for fun, they might even go over and weigh them just for their own bragging rights. That's what I would do if I was in their position. Let's see, handfuls of rocks. That's fun to see how much they were able to bring up, even though they were not able to get it back to the starting point. So looking ahead, great job, New Mexico Tech and University of Utah. Looking ahead, our next run is going to be just a single robot instead of two. It's going to be the University of Rochester. After that, we will have our final run, which is going to be Arkansas and Purdue. So don't go anywhere because we have more of NASA's Lunabotics 2022 competition coming up in just a few minutes.
Innovation is at the core of our work at NASA. It determines where we're going and how we'll get there. Innovation created the first mission to Mars. It allowed us to study the solar system beyond the sun's influence, and it sent the first humans to the moon. Innovation helps NASA take giant leaps in our work on space exploration, aeronautics, and Earth science research. It saves money with an idea for how to solve a problem, but that is only years of hard work by teams of people working together. It is more than imagining a solution. It is making that solution a reality. Innovation is building, shaping, and refining an idea. It is using existing technology in new ways to maximize impact. And true innovation moves beyond linear growth. True innovation is exponential growth. It is finding new spaces to grow into, new niches to explore, new resources, and new ideas. It is connecting the dots. At NASA, we know innovation isn't created by one person alone, and we know it isn't created by one team alone. That's why we propel our mission through open innovation. Open innovation invites the best creative minds from across the world to work with us to solve some of our most complex problems. We know the more minds we have working on a problem, the better chance we have of true innovation, of exponential growth. Open innovation amplifies the work we do. It solves problems in ways we could never imagine, and it develops solutions that can change the world.
Looks like we've got the University of Rochester team putting their robot into the B side of the arena. There will not be a robot running on the A side of the arena for this run. And this is the second to the last run of the day. After Rochester, we should see Arkansas and Purdue come into the arena and perform their second and final run of the competition. And that will be the end of our schedule for our first group of teams, which ran yesterday and today. And obviously, we won't be able to give any results after our last run today because really that's only half of our full Lunabotics competing teams in our competition this year. We've split our competition into two groups. Group 1, which you've been watching yesterday and today, and Group 2, which are going to show up tomorrow. We won't be live streaming tomorrow. Teams are going to show up tomorrow, get all set up, and then we will live stream on Thursday and Friday the Group 2 runs. Just to give you a tease about the Group 2 teams that we will see Thursday and Friday, we are expecting to see on Thursday and Friday Auburn, the College of DuPage, Lone Star College, Cy-Fair, Marquette University, Montana Tech, North Dakota State University, Oakton Community College, San Diego State University, Sonoma State University, South Dakota School of Mines and Technology, Temple University, the University of Illinois at Chicago, the University of Kentucky, the University of Maine, the University of Nebraska-Lincoln, the University of New Hampshire, the University of North Dakota, the University of North Florida, the University of Portland, the University of Virginia, Worcester Poly Institute, WPI, and last but not least, Youngstown State University. Those are all the teams that we have scheduled and expect to see and expect to live stream the two competitions runs of all of those teams on Thursday and Friday. But right now, we're going to turn our attention to Rochester, the University of Rochester, who are in the arena right now, putting the final touches and powering up their robot, powering up their router, powering up their computers in the control room, and checking the data, checking the commands, making sure everything is hooked up and running and checking out okay before we start their run. As we wait for this Rochester team to finish their activation and check out of the robot and start their 15-minute run, I want to take a few minutes to thank all the different groups, different organizations, and different individuals that have helped plan and organize and put on this event. The NASA Kennedy Space Center has a lot of people that work there that have taken a lot of time and a lot of energy, spent a lot of resources getting this event planned and organized and run. Their Office of STEM Engagement and also their Office of Public Affairs and Public Outreach have spent a lot of time and energy getting this event to be what it is today. Also, Delaware North and the KSC Visitor Complex has graciously allowed us to perform our event on their property and use a lot of their resources, including the Astronaut Memorial Foundation and the Center for Space Education, which is the building, the facility that we are actually using within the Kennedy Space Center Visitor Complex. Secor Strategies, Paul Secor and his company have done an amazing amount of work working on program management and logistics and virtual events and event coordination and numerous other tasks that we could not have lived without. The entire Lunabotics planning team, which meets regularly throughout the year, not just leading up to the event, but meeting throughout the year and planning and organizing this event. And especially the event staff that actually volunteers during their what would normally be their normal day job. They basically take a break from their normal day job in order to volunteer their time and their energies to support this event during its actual run. And all of the both the event staff and the event volunteers that are working here tirelessly for long hours all week long. We just really want to thank everyone that has contributed to the planning and the organization and the actual event implementation itself. Now we are probably just a few moments away from seeing this Rochester robot perform its 15-minute run in this simulated lunar regolith or lunar soil here in our Artemis Arena. All these students from all these teams who are competing here this week, this is just the tip of the iceberg. This is the very last portion of an entire school year for most of these teams. The rules for each year's Lunabotics competition are usually announced in the summertime before school starts or thereabouts. So these teams get themselves organized in the fall. They start planning their robot design once the rules are released. They spend the entire fall semester. They spend nearly the entire spring semester designing and building and testing, fixing things that break, retesting, changing designs that don't quite work, retesting. It's a very long, very detailed, very resource intensive process for these teams. And what you're seeing when these teams only get two chances, two 15-minute runs for each of these teams, is really just the very tip of the pencil. It's very, very small amount of the overall process that these teams have undertaken over the last 10 or so months. It looks like this 15-minute run has already started for this Rochester team. And so far, I have not noticed any movement from this robot. So hopefully we see some movement soon, as this 15-minute run has already begun. I learned something kind of fun about the University of Rochester when I was doing a little bit of internet searching before the competition started. The University of Rochester actually spent its first entire decade running out of an old hotel in downtown Rochester. During the school's very first year, Ralph Waldo Emerson was quoted as saying the following about this school. He said, "They had bought a hotel, once a railroad depot, turned the dining room into a chapel by putting up a pulpit on one side, made the bar room into a literary hall, and made the chambers or rooms into recitation rooms, libraries, and professors' apartments. They had brought a busload of professors down from Madison, bag and baggage, called in a painter, and sent him up the ladder to paint the title University of Rochester on the wall. And they had runners on the road to catch students. And they were confident of graduating a class of 10 by the time the green peas are ripe." I just really loved that quote and that visual when I read that on Wikipedia about the start of the school, especially the part about the runners that were sent out onto the road to catch new students. Still waiting for some movement from this Rochester robot. We're 5 minutes into their 15-minute run. All right, we are now 7 minutes into this 15-minute run for Rochester, and sadly, I have not noticed any movement out of this robot. I presume the students are working feverishly in the control room, in the control center, looking at their data and trying to see if they can fix whatever their issue is. This Artemis Arena that you're looking at in the video here is basically brand new. This is the first time this Lunabotics 2022 event is the first time this arena has been used, and the plan is to use this arena for more than just the Lunabotics events. We have all kinds of great ideas and great plans that we're going to try to implement as soon as we finish Lunabotics this year, in order to try and use this facility. We got movement. The robot, it's almost 10 minutes into a 15-minute run, and the Rochester robot has lunged out of its starting position. So what I was saying was that this arena, you'll notice that, well, for those that are really familiar with the Lunabotics competition in the past, our two side-by-side arenas in the past were basically two separate, very large bins, metal bins that are basically a lot like garbage dumpsters, very large garbage dumpsters side by side, and that's what basically made up our two courses, our two runs, our two arenas. And when we designed this indoor arena, we designed it to be more square and less rectangular, without a hard wall in the middle, so that even though the Lunabotics competition requires this wall between the two arenas, future events or future uses of this space might not want a wall in between. They might want to use that whole entire space, and so that's why we've got this this soft, flexible tennis court net looking temporary wall installed between our two arenas. That gives us a lot of flexibility for using this facility for other events that require a bigger space or a bigger arena. Well, that was kind of exciting when the Rochester robot a couple minutes ago lunged out of the starting position. It headed straight for that berm, which I'm not sure, due to its low ground clearance, I'm not sure this particular robot would be able to make it across that berm. but as suddenly as the robot lunged out of the starting gate, it stopped just as suddenly, and I have not seen it move since. And we're 12 minutes into this 15-minute run. Less than 3 minutes remaining for Rochester to figure out what their problem is, and potentially correct it. Now, at the end of Rochester's run, here in just a few minutes, my schedule in front of me, which is live and updating electronically, it only tells me that Purdue is running next. So I'm not sure if we lost Arkansas for some reason, and they're not able to compete. But definitely stay tuned, because Purdue is going to be running next, and Purdue is going to be our last run of the day and the last run of the teams that are competing here yesterday and today. One minute remaining in this run for Rochester. Sadly, time has run out for the University of Rochester, but kudos to the team for getting this amazing-looking robot all the way to this point. And it obviously worked for a little bit, so there was some success there. Not the full success that the team was hoping for, but kudos to the team for getting this far. They should be proud of what they've accomplished. Next up, we're going to have Purdue University, and I think they're going to be running alone, but we will find out soon.
NASA's Artemis program is working to return humans to the surface of the moon for long durations. Then we will use what we learn to take the next giant leap, sending the first astronauts to Mars. And these future human explorers of tomorrow will need to eat. But making food in space is not easy as pie. That's why virtually all the food astronauts currently eat in space is sent from Earth. But what about future astronauts on years-long deep space missions? They'll have to bring everything they'll need with them. Not only the food ingredients themselves, but they'll also need energy, water, and other materials to transform those ingredients into nutritional and tasty meals that they will actually want to eat. That's why NASA and the Canadian Space Agency launched parallel competitions, the Deep Space Food Challenge, to reach out to innovators from across the globe to compete for prize money for anyone who can come up with and build novel food production technologies that could be used in space. Lots of new design ideas were brought to the table during the first phase of this competition, from dehydrated foods to cultivated plants and fungi. Several designs were selected as winners of Phase 1. But now, in Phase 2 of this competition, teams from across the globe are working to build and demonstrate a working food production technology prototype, and even provide samples of their edible creations for expert space taste testers to approve. Not only could this transform space travel, but it could also transform food systems right here on Earth, helping to resolve food insecurities and scarcities across our own planet. At NASA, there can never be too many cooks in the kitchen, so follow along as we all work together to feed interplanetary humans of tomorrow in the Deep Space Food Challenge.
Stay tuned to NASA's Lunabotics 2022 live stream because our very last run of the day, our very last run of Group 1, which is the portion of our teams that competed in the first half of the week, Monday and Tuesday, our last run is about to come into the arena and compete. This last run is going to be Purdue University. And so that team should be arriving into our Artemis Arena area momentarily. So don't go anywhere. Continue watching Lunabotics 2022 edition. Watching a live feed from the RoboPit area of Lunabotics 2022 Collegiate Robotic Mining Competition. And we were saying earlier that Purdue was coming up next. And then we saw some really excited activity from the Rochester team as they came running back into the RoboPits with their robot, working feverishly on it as you see them there in the center of the screen. So I went into the RoboPits to get the skinny from the pit boss. And what I was told that was that Purdue is not able to run. They have bowed out of their second attempt. And it turns out that Rochester actually did not have their first attempt yesterday, and so the Rochester run that we just saw about 20 minutes ago, the judges have deemed that will be scored as their first attempt, and they're letting the Rochester team turn around and run their robot second attempt momentarily. So let's give Rochester a little bit of time to get their robot turned around, get whatever issues that they had in their first attempt worked on and fixed. And we will be back in just a few minutes with the final run of Monday and Tuesday's half of NASA Lunabotics robotic mining competition. So don't go anywhere. We will be right back.
other things, not because they are easy, but because they are hard.
So, late breaking news at the NASA Lunabotics 2022 event. We're being told by various sources that our final run of the day is going to include Milwaukee School of Engineering on the A side of the arena and the University of Rochester on the B side of the arena. It should be noted that Milwaukee School of Engineering already had their 2 official competition runs. This is a demonstration run. They will not be scoring any points for this run. I'm not. And just in case anybody who's watching is under the impression that we will be giving out results or standings at the end of the day today, we will not. At the end of the day today, we will only be halfway through our entire field of Lunabotics 2022 teams, and so we will not be announcing or publishing any results or standings. There's a lot of work going on behind the scenes with our judges and all of their evaluation criteria and all of their judging criteria, and they will. It's my understanding that results and standings will only be published after our competition is completely done, meaning after Thursday and Friday, and possibly even the week after will be the time where we will actually see published results. And for those students who are competing in this event, I'm sure they're all fully aware that the actual awards ceremony will be virtual this year, and it will be held not this week, not Friday at the end of the competition. It will actually be held the following week. But the students and their sponsors should already have those details about the award ceremony, so that they will be sure to set aside time and know the correct place on the internet to find that award ceremony as it's broadcast on the internet for them. In the meantime, we are anxiously awaiting our final run of the day. We can see students, possibly Rochester students by the color of their shirts, getting their personal protective equipment on at the far end of the room, at the far end of our robo pits. And so we're going to have one final run today to close out the first half of our Lunabotics 2022 event. The final run is going to have Milwaukee School of Engineering and the University of Rochester both running in our arena in just a few minutes, hopefully. The robot you're seeing on the screen, about to be lifted into the arena, is the Milwaukee School of Engineering robot. Now, this team has already completed both of their official competition runs, but they've done some work on their robot, and they have requested the judges to allow them to perform a demonstration run that will not be scored. So this is just to test out their robot and see how things are working, and it will not be used for scoring for the team of Milwaukee School of Engineering. And we also see the University of Rochester team is starting to bring their robot into the arena for their second attempt, I believe. We can see that both teams are activating their robots now. Milwaukee School of Engineering on the right-hand side of the screen in Arena A, and University of Rochester on the left-hand side of the screen in Arena B. Well, it would appear that we have our two teams robots activated, checked out, and ready to go. On the screen, you'll see Milwaukee School of Engineering's robot at the bottom of the screen and the University of Rochester's robot at the top of the screen. So hopefully we will see these robots start their 15-minute runs here momentarily. All right, our 15-minute timer is counting down, and the Rochester robot has started moving out of the starting box. Now, this Rochester robot definitely has some power in its drive system. It is throwing rooster tails into the air when those wheels power, but it does not look like it's making much, if any, progress. It may have high centered, and which might not be allowing the wheels to get enough traction to move the robot. Now, we have seen robots previously in this competition which have appeared to have gotten themselves high centered and lose traction. And we have seen more than one instance where a team was able to manipulate their digging system, for example, or manipulate some other system on board the robot in order to help nudge or push or lift the robot. And we're noticing some movement on the Milwaukee robot at the bottom of the screen, and I just realized that this robot is up on blocks. So they're just testing, probably going to be just testing all of their motors, all of their actuators, all of their mechanical motion systems without actually driving the robot around in the simulated lunar regolith is what it looks like their plan is. Again, the robot at the bottom of the screen, which is the Milwaukee School of Engineering robot, they've already completed their 2 runs, and they have requested to have some time in the bin for a demo only, no points, a run that is not for points. And we did see the Milwaukee's wheels turn just a little bit ago. Meanwhile, Rochester got nearly half of the robot out of the starting zone before it seemed to have sunk down into the light, fluffy regolith simulant. And now we can see their digging mechanism in the middle of the robot moving back and forth. I believe that is a large. I believe their digging mechanism is a large rotating bucket drum with very large buckets or teeth sticking out of it that I presume can raise and lower. From this camera angle, we can see the Rochester robot's wheels spinning. We can see the robot moving just a little bit when those wheels spin. Making forward progress. It could be a digging wheel, the digging bucket drum in the middle of the robot that might be dragging the ground. We're 6 minutes into this 15-minute run. Seems like we saw the front wheels on the Milwaukee robot turn earlier. I don't remember seeing the rear wheels turn, but I might have just not noticed. And I haven't noticed any other mechanisms on the Milwaukee robot make any movement so far. 7 minutes in, 8 minutes to go. So now I'm noticing that the wheels of the Rochester robot are spinning and no dirt appears to be flying out anymore, which kind of implies that those wheels are free spinning in free air and are no longer making contact with the ground whatsoever, which is a really tough place to recover from, sadly. But the students in the control room are obviously not giving up on this robot. So I just want to point out that all of the robots that we've seen that have had mobility issues in this lunar soil simulant that fills our Artemis arena have basically shown and proven again and again that driving across on top of this light fluffy powder and not sinking in is one of the bigger challenges of actually operating on the moon. And so even though we've seen a lot of robots, a lot of teams struggle getting their robot all the way down to the digging area, these struggles actually can be viewed as lessons that tell us what designs don't quite work and help us rule out certain designs and help us narrow in on the best designs that we need to be using to send robots to operate and work on the moon. Milwaukee's robot has raised its digging mechanism. You can see under its digging mechanism is a hopper, a bin, a dump bed that is full of holes. So what you can imagine is if the buckets that are on the left of the screen, the front of the robot, if those were coming up and around and over the top of that digging arm, that digging mechanism, that they would be dumping each load directly into that hopper that has the holes in it. And I presume underneath that hopper is just free space, a space for the small particles to fall through back down to the surface. And we can see rotation now on the Milwaukee digging arm or bucket ladder system. Looks like it's probably chain driven. Each bucket appears to be made out of metal. That would be the reverse direction. That would not be the digging direction for that particular implement. It almost looks like there are signatures on the bottom of each one of those, several of those digging buckets. I wonder if the students were given the opportunity to autograph their robot. Okay, there. I just realized they're lowering the Milwaukee team was actually lowering their digging system as it was rotating, and it finally actually hit the ground and did not start digging because it's rotating in the wrong direction, but actually ended up knocking the robot off of its blocks. Again, this Milwaukee robot is not competing for points in this run. And it looks like, sadly, Rochester was never able to get out of this spot that they got themselves dug into. And it looks like our 15 minutes has just now expired for these two teams. So that is going to end the first half, day 1 and day 2 of the 2022 NASA Lunabotics Robotic Mining Competition, a collegiate event that brings college and university teams from all over the country to converge here at the Kennedy Space Center Visitor Complex in Florida once a year after spending the entire school year designing and building and testing and breaking sometimes and fixing and retesting and sometimes realizing that something doesn't work and having to redesign it and rebuild it and retest it. This is all part of the engineering design process. The students are learning. Sometimes they're learning the hard way about what doesn't work and what does work. And so this concludes day 2 of a 4-day event. We will not be live streaming tomorrow, but tomorrow will be used to switch out the teams and bring in our Group 2 set of teams, the second half of our 2022 group of set of teams that are competing this year. And what we'll do once we get all the teams set and all set up in their Luna pits on Wednesday, on Thursday, we will live stream again. Our live stream on Thursday is going to start at noon Eastern Time. You can go to our, there are 2 places where you can find our link to our live stream on Thursday. You can go to, on Thursday morning, you can go to nasa.gov/Lunabotics, and the link to our Thursday live stream should be there right on our Lunabotics webpage at nasa.gov/Lunabotics. If you go to our Facebook page by going to Facebook and searching for NASA Lunabotics, you can scroll down just a page or two and you'll be able to see a post where our project manager has posted all 4 links to all 4 days webcasts. And you could even go back and watch yesterday's webcast. You could, after we sign off here, you'll be able to watch today's. All these links should stick around forever on YouTube, and you'll be able to use all of the YouTube features that you're used to using, like sharing the URL or sharing a particular spot to start in the URL. So we want to thank everyone for watching, especially the 53 who held on all the way to the very end of today's event to see the very end. of the last two teams to compete today. We thank you all, and we will see you all on Thursday, noon Eastern Time. And I was just reminded, that was a really good catch. I was reminded that I want to read off the names of the teams that are going to be competing on Thursday and Friday, because you're going to want to come back and watch these teams. Even if your school has already competed Monday and Tuesday, you're really going to want to come back and watch Thursday and Friday, because what the teams that we expect to compete on Thursday and Friday are as follows: Auburn, DuPage, Lone Star College, Marquette University, Montana Tech, North Dakota State, Oakton Community College, San Diego State, Sonoma State, South Dakota School of Mines and Technology, Temple University, the University of Illinois at Chicago, the University of Kentucky, the University of Maine, the University of Nebraska-Lincoln, the University of New Hampshire, the University of North Dakota, the University of North Florida, the University of Portland, the University of Virginia, Worcester Polytechnic Institute, and Youngstown State University. So if that list of teams doesn't get you excited, I don't know what will. So please come back and watch our live stream on Thursday and Friday, and we can't wait to see these teams compete, and we hope that you will join us. For now, signing off from NASA's Kennedy Space Center Visitor Center, this has been NASA's Lunabotics 2022 competition. See you soon.